Picture a stream of energy so immense it could cross entire galaxies in a single blast, a torrent of plasma and radiation spewing from the edge of a gravitational abyss from which not even light can escape. These are black hole jets, cosmic fire hoses of raw power that rage against the very darkness from which they are born. What are these spectacular structures, and why, despite decades of observation, do they continue to defy our most fundamental understanding of physics? They are not merely distant curiosities. They are some of the most energetic and enigmatic phenomena in the entire cosmos, capable of shaping the fate of whole clusters of galaxies, yet their origins remain wrapped in layers of profound mystery. We look at them and see the universe's ultimate paradox, incomprehensible power erupting from total oblivion. For years, astronomers have trained the world's most powerful telescopes on these brilliant, slender beams, and with every new discovery, the mystery has only deepened. Each jet seems to carry its own set of rules, its own unique signature of bizarre behavior that challenges our models and pushes the boundaries of known science. From their mind-bending speeds to their unexpected structures and baffling energy sources, black hole jets present a puzzle that touches upon the most extreme conditions the universe can produce. They are cosmic laboratories where gravity, magnetism, and matter interact in ways we are only beginning to glimpse, and every answer we find seems to generate two new, even more compelling questions. That is precisely why we've embarked on this journey, to pull back the curtain on these extraordinary engines of creation and destruction. In the exploration that follows, we will dive deep into 40 of their most puzzling and unexplained features, each one a testament to just how much we have yet to learn. From jets that curve and twist in impossible ways to outbursts of energy that appear to arrive before they are triggered, we will uncover the riddles that have left even the most seasoned researchers searching for new physics. This is not just a catalogue of strange facts. It is an invitation to witness the cutting edge of human discovery, to stand at the frontier of knowledge and gaze into the unknown. So prepare to venture into the heart of one of space's greatest ongoing mysteries, where every revelation invites more wonder and every beam of light holds a secret waiting to be uncovered. And so we arrive at our very first mystery, a feature so fundamental to the identity of black hole jets that it underpins nearly every other puzzle we will discuss: the origin of their ultra-relativistic speeds. To say these jets are fast is a staggering understatement. The charged particles screaming along these cosmic conduits are accelerated to over 99.9% of the speed of light. At such velocities, the very concepts of time and space as we understand them begin to warp and break down. The energy required to fling matter to this brink is almost unimaginable, equivalent to converting the entire mass of multiple suns into pure, unfettered kinetic energy. This isn't just a gentle push, it's a cataclysmic launch from the most extreme environment in the universe. So, how is this even possible? The leading theoretical framework points to a truly elegant mechanism known as the Blandford-Zienagic process. Picture the supermassive black hole at the center of it all, spinning at a fantastic rate. This rotation doesn't just drag space-time around with it, it also twists the black hole's immensely powerful magnetic field into a coil of unimaginable tension. The theory suggests that this spinning magnetic field acts like a cosmic slingshot, extracting rotational energy directly from the black hole itself and using it to fling ionized plasma outward in two narrow, oppositely directed beams. It's a beautifully efficient idea, turning the black hole's own spin into the engine that powers the jet. Yet for all its elegance, the Blandford-Zienagic process remains just that, a theory, and one with significant gaps at that. The immense challenge is that the exact acceleration zone, the very heart of the engine where particles are whipped up to these fantastic speeds, is thought to reside terrifyingly close to the black hole's event horizon, a region permanently hidden from our view. It's like trying to understand the intricacies of a car engine by only observing the exhaust fumes miles down the road. Our observations show jets that are far more structured and contain much more energetic particles than most simple models predict. What precise, microscopic interactions between particles, magnetic fields, and turbulent plasma are at work in that hidden crucible? How is the energy transferred so efficiently, and why do some particles get this monumental boost while others are left behind? The process gives us a compelling sketch of the power source, but the detailed blueprint of the accelerator itself remains one of the greatest unsolved problems in high-energy astrophysics. This astonishing velocity immediately leads us to our second profound mystery, one that lies at the very heart of what these jets are made of. If the speed of the jet is the how, then its composition is the fundamental what, and this question is far from settled. We know that jets are composed of a superheated, magnetized plasma, a fourth state of matter where atoms are torn apart into a soup of charged particles. But are these particles primarily lightweight electrons and their antimatter counterparts, positrons? Or are they heavy protons and entire atomic nuclei known as ions? This seemingly simple question, the plasma composition problem, is a monumental puzzle because the answer dictates almost everything else about the jet's behavior, from its total power to its very purpose in the cosmic ecosystem. The distinction is not merely academic, it represents a chasm in our understanding. Picture two different types of fire hoses. One is spraying a stream of lightweight ping-pong balls. The other is blasting out heavy cannonballs. Even if both streams are moving at the same incredible speed, the amount of energy required to propel the cannonballs is exponentially greater. This is the core of the dilemma. If the jets are made of lightweight electron-positron pairs, they are still phenomenally powerful, but the energy demands on the black hole system are somewhat less extreme. Such a composition would suggest the jets are more like focused beams of pure energy and momentum, excellent for heating the surrounding space but perhaps carrying less raw mass. On the other hand, if the jets are predominantly protons and ions, the implications are staggering. It means the black hole engine is not only accelerating particles, but also lifting and launching tremendous amounts of heavy matter from the depths of its gravitational well. The total kinetic energy contained in such a jet would be orders of magnitude higher, transforming our estimate of the black hole's efficiency from merely impressive to almost unnaturally supreme. A heavy jet would also carry far more influence, plowing through intergalactic space like a cosmic bulldozer and depositing mass and energy that can literally clear out vast regions and halt the birth of new stars in entire galaxies. The frustrating brilliance of these jets is that from our distant vantage point, they can appear deceptively similar. Our telescopes measure the light they emit, which comes predominantly from electrons and positrons spiraling at near light speed along magnetic field lines, a process known as synchrotron radiation. It's like trying to determine what a truck is carrying only by studying the glow of its headlights. We can see the light produced by the electrons, but we often cannot directly detect the potentially invisible, heavier protons that might make up the bulk of the mass. This leaves us with a persistent ambiguity. Some jets, particularly those from supermassive black holes in distant quasars, show indirect evidence of being light, while others, like the one emanating from the relatively nearby galaxy M87, seem to carry the hallmarks of a heavier, more powerful load. This fundamental uncertainty ripples through every model we try to build. Without knowing the composition, we cannot accurately calculate the jet's true power output, its effect on its surroundings, or even the basic mechanisms that collimate it into such a narrow beam. It forces us to consider the possibility that there is no single answer, that different black holes, depending on their spin, their magnetic field structure, and the properties of the material they are consuming, might manufacture jets with entirely different recipes. The mysterious composition, therefore, remains a primary hurdle, a basic piece of information that we desperately need to peel back the deeper layers of this cosmic enigma. Now consider the sheer scale of the journey these jets undertake. They are launched from a region smaller than our solar system, yet they can travel outward for millions of light years without spreading out and dissipating like a puff of smoke. This brings us to our third great puzzle, their incredible long-range collimation. How do these torrents of plasma stay focused into such impossibly narrow, pencil-straight beams across distances that are almost impossible to comprehend? It's the difference between a laser pointer that stays coherent for miles and a simple flashlight beam that scatters and fades after just a few feet, only on a scale that dwarfs entire galaxies. The very existence of these structures over such vast distances defies simple intuition. Any natural outburst of energy and matter would be expected to expand, to fan out into a wide cone as it travels through the emptiness of space. Think of a hose spraying water into the air. The stream starts tight but quickly breaks up into a diffuse spray, yet black hole jets do the opposite. They remain tightly wound, often with an opening angle of just a few degrees, sometimes even less. They can traverse intergalactic space, plowing through the thin gas that exists between galaxies, and still emerge on the other side as a coherent, focused beam. This suggests there is a continuous, active process at work, a kind of cosmic guidance system that constantly pinches the jet and prevents it from unraveling. For a long time, the prime suspect for this feat of cosmic engineering has been the magnetic field. The prevailing idea is that the same coiled magnetic fields that help launch the jet also act as an invisible sheath, a constricting tube of magnetic pressure that wraps around the flowing plasma. This is known as the magnetic hoop stress model. Picture a flexible garden hose. The water wants to spray out in all directions, but the tough outer hose contains it and directs the flow. In a similar way, the magnetic field lines are thought to provide a confining structure, pinching the plasma inward and maintaining the jet's incredible narrowness. It's an elegant and powerful concept, and for the regions of the jet closest to the black hole, it likely plays a dominant role. However, as we observe jets extending far beyond their host galaxy, the magnetic field alone may not be enough. The field's strength naturally weakens with distance, and at some point its confining power should diminish, allowing the jet to finally balloon outward. But for many jets, this doesn't happen. This has led scientists to propose a second crucial actor, the external environment. The intergalactic medium, while incredibly tenuous, is not a perfect vacuum. It exerts a gentle but constant pressure on all sides of the jet. Some models suggest this external pressure acts like a wall, providing the necessary confinement to keep the jet focused over its epic journey. It's a delicate balance. Too much pressure and the jet would be crushed, too little and it would expand uncontrollably. Yet even with these two mechanisms, the full picture remains frustratingly incomplete. We observe jets that remain collimated in regions where the external pressure is believed to be far too weak to provide any meaningful confinement. Other jets show intricate, stable structures like internal filaments and sharp edges that are difficult to explain with a simple combination of magnetic fields and ambient pressure alone. This suggests there may be complex internal dynamics at play, perhaps involving turbulence or interactions between different layers of the jet flow that somehow contribute to its self-confinement. The precise recipe, the exact balance of magnetic forces, external pressure, and internal hydrodynamics that conspires to create these perfect cosmic spheres, is one of the most active and unresolved areas of research in astrophysics today. Just when we think we've grasped the immense symmetry of these systems, where two opposing jets blast out with equal ferocity, the universe presents us with a glaring asymmetry that challenges our very perception of balance. Our fourth unexplained feature is the mystery of the one-sided jet. In many systems, one jet is not just slightly brighter, but dramatically more powerful and prominent than its counterpart. While sometimes this is a simple trick of perspective where a jet pointed almost directly at us appears artificially bright due to a relativistic effect, this is not the whole story. There are numerous cases where the imbalance is intrinsic, a true and profound lopsidedness in the engine itself, suggesting that something fundamental is broken in our expectation of cosmic symmetry. Imagine a powerful tug of war where both teams are supposed to be perfectly matched, yet one side is effortlessly pulling the entire rope its way. That's the kind of fundamental imbalance we're observing. For a black hole to produce such a disparity, the conditions around it must be fundamentally uneven. One compelling line of inquiry points directly to the black hole's spin. The spin is thought to be the ultimate power source, and if its axis of rotation is misaligned with the surrounding accretion disk, the swirling platter of infalling matter, it could create a chaotic and unbalanced environment. In such a scenario, the magnetic fields anchored in the disk and the black hole itself could become twisted into a configuration that favors launching material more efficiently in one direction over the other. It's like a misaligned washer on a powerful drill. The vibration and energy output become uneven and unpredictable. Another possibility lies in the accretion disk itself. These disks are not always the serene, smooth structures we often picture. They can be turbulent, prone to instabilities, and even warped. If a dense clump of material, perhaps from a disrupted star, falls onto one side of the disk, it could trigger a localized surge in accretion. This would temporarily pour more fuel onto the black hole's engine from that specific direction, potentially powering up the jet on that side while the other jet, starved of equivalent fuel, remains comparatively faint. This would create a temporary but observable asymmetry, a flickering imbalance in cosmic power. Yet another factor could be the environment through which the jets are traveling. A jet plowing into a denser cloud of interstellar gas would have to work harder, its forward progress slowed and its energy dissipated as heat and light, making it appear brighter and more turbulent. Meanwhile, its twin, escaping into a clearer, lower density region, might stream away almost invisibly. In this case, the asymmetry isn't in the launch mechanism itself, but in the external obstacles the jets encounter, like two runners on different tracks, one struggling through mud and the other sprinting on a paved road. The profound challenge is that while we have these individual theories, no single one of them satisfactorily explains all the observed cases of one-sided jets across different types of black hole systems. Some jets show asymmetries that persist for timescales too long to be explained by a temporary disk instability, while others exist in environments that appear too uniform for external pressure to be the sole culprit. The black hole spin theory is powerful, but it's incredibly difficult to measure the spin and its alignment directly. This leaves us with a gallery of lopsided cosmic engines, each one potentially telling a different story about the complex and often messy physics of accretion and jet formation. The one-sided jet mystery forces us to accept that the perfect symmetry we often attribute to cosmic objects may be more of an ideal than a rule, and that true understanding lies in unraveling the unique, chaotic history of each individual black hole and its immediate surroundings. As we continue to follow these jets across the cosmos, we encounter a phenomenon so counterintuitive it seems to break the universe's ultimate speed limit. This is the astonishing illusion of superluminal motion, where bright blobs or knots within a jet appear to race outward at speeds exceeding that of light itself. It's a trick of perspective and physics that has captivated and confused astronomers since it was first observed, offering a direct and dramatic demonstration that in the realm of black holes, seeing is not always believing. The secret to this cosmic sleight of hand lies in the combination of two key ingredients: the jet's genuinely staggering velocity and the finite, unchanging speed of light. Picture a single bright knot of plasma that has been energized by a shock wave within the jet, sent streaming toward Earth at 99.9% of light speed. As this blob travels, it emits light in all directions. Now, imagine the blob is moving at a very slight angle, almost directly along our line of sight. The light it emits at a point closer to us has a shorter distance to travel to reach our telescopes than the light it emits a fraction of a second later, when it has moved even closer. The result is that the time interval between these two bursts of light is compressed from our perspective. We measure the blob's apparent motion across the sky based on the arrival times of this light, and because the second pulse had less distance to cover, it arrives much sooner than expected. This makes the blob appear to have traversed a vast distance in an impossibly short time, calculating out to a velocity that seems to break the light barrier. This purely geometric explanation is beautifully consistent with Einstein's theory of relativity, which firmly states that no information or matter can travel through space faster than light. The superluminal motion we observe is a projection effect, a cosmic mirage caused by the jet's material chasing its own light. It's analogous to a supersonic jet flying low over your head. The sound waves it produces are compressed, creating a sonic boom that seems to arrive from a point ahead of the jet's actual position. In the case of the black hole jet, we are witnessing a light boom, an optical illusion born from relativistic speeds. However, while the basic physics of the illusion is well understood, it introduces a profound layer of complexity when we try to decipher the jet's true internal dynamics. The very fact that we observe these superluminal knots tells us that the jet is not a smooth, continuous flow, but is instead riddled with internal shocks and energetic disturbances. These bright blobs are likely sites where faster-moving material in the jet's core plows into slower-moving plasma ahead of it, creating violent collisions that accelerate particles and generate intense bursts of radiation. But this creates a significant interpretive challenge. The observed superluminal speed is not the true physical speed of the plasma, but rather the apparent speed of a pattern, a shock front moving through the jet. This distinction is critical. It's the difference between measuring the speed of a wave crashing onto a beach and measuring the speed of an individual water molecule within that wave. The wave pattern can travel much faster than any single molecule. In the context of the jet, a shock wave can propagate through the plasma at a significant fraction of light speed, creating a brilliant knot that appears to move superluminally, even if the underlying plasma flow itself is slightly slower. This makes it extraordinarily difficult to pin down the jet's true bulk velocity and energy. Are we watching the actual plasma, or are we just tracking the flickering of a luminous pattern running along its structure? Furthermore, the presence of these features forces us to confront the jet's instability. What triggers these internal shocks in the first place? They could be the result of fluctuations in the accretion rate, a sudden gulp of matter falling onto the black hole that injects a fresh surge of power into the base of the jet. This surge then travels outward, eventually catching up with previously ejected, slower material. Alternatively, the instabilities might be inherent to the jet launching mechanism itself, with the magnetic fields at the heart of the engine periodically reconnecting and releasing enormous bubbles of energy. Each superluminal knot we detect is a fossil record of a past eruption from the central black hole, a time capsule of a violent event that occurred millions of years ago. Decoding their true nature is essential because by misinterpreting an apparent speed for a real one, we could be making fundamental errors in calculating the immense power these cosmic engines are able to wield. Now we reach the very heart of the matter, the engine room of this cosmic phenomenon, the central black hole itself. It's here, in the chaotic space just outside the event horizon, that the raw power for the jet is forged. But this isn't a simple one-size-fits-all engine. The specific properties of the black hole, its mass, its ferocious spin, and the rate at which it consumes matter act like a control panel, directly dialing the jet's power, stability, and even its very existence. Understanding this connection is fundamental, yet it forces us to confront one of the most difficult measurements in all of modern astrophysics. Let's start with the most straightforward parameter, mass. We have developed reliable techniques for weighing supermassive black holes, often by observing the orbital speeds of stars or gas whipping around the galactic center. This mass sets the overall scale of the system. A more massive black hole has a deeper gravitational well and a larger event horizon, which generally allows for a more powerful engine. But mass alone is not the trigger. We find plenty of incredibly massive black holes that are quiescent, sitting quietly without producing any visible jet at all. This tells us that while mass provides the potential for power, it is not the switch that turns the jet on. That crucial switch appears to be the black hole's spin. The spin of a black hole is a concept that stretches our intuition. We're not talking about a solid object rotating like a planet. Instead, it's the very fabric of space-time itself that is being dragged around the black hole in a swirling vortex, an effect known as frame dragging. This rotation is the ultimate battery. According to the leading theoretical models like the Blandford-Zenagic process we discussed earlier, a spinning black hole can transfer its rotational energy to the surrounding magnetic fields, which then act as cosmic transmission belts, flinging plasma outward to form the jet. A faster spin means a more powerful battery capable of launching a more energetic and persistent jet. In fact, some models suggest that for a truly powerful, continuous jet to form, the black hole must be spinning at a significant fraction of its maximum possible rate. This brings us to the monumental challenge. How do you measure the spin of an object that emits no light, an object defined by its ability to trap all information? We cannot see the spin directly. Instead, we must be incredibly clever, inferring it through indirect and complex methods. One primary technique involves studying the inner edge of the accretion disk, the swirling maelstrom of superheated gas that feeds the black hole. The faster a black hole spins, the stronger its gravitational grip, pulling the inner edge of that disk closer to the event horizon. By carefully analyzing the X-ray light emitted from this searingly hot inner disk, astronomers can look for subtle distortions in its spectrum, a telltale signature of light struggling against the warped space-time of a rapidly rotating black hole. It's like trying to determine the speed of a spinning vortex by studying the patterns of debris caught at its edge. Another method involves measuring the intensity and temperature of the X-ray emission itself. A faster spinning black hole, with its accretion disk reaching deeper into the gravitational well, is predicted to produce a hotter, more luminous inner disk. By comparing these observations with sophisticated computer simulations, scientists can estimate the spin. Yet a third, more recent technique relies on detecting a faint, shimmering echo of light known as X-ray reverberation. When a flare of high-energy light erupts from the very center of the system, it illuminates the inner accretion disk, and the specific time delays in the echoes we receive can map the geometry of that space, revealing just how close the disk gets to the event horizon. Each of these methods is a masterpiece of scientific deduction, but they all come with significant uncertainties and potential pitfalls. The X-ray spectrum can be contaminated by intervening clouds of gas, making the signal murky. The assumed structure of the accretion disk might not always be correct. If the disk is warped or puffed up, our spin estimates could be wildly off. Furthermore, these techniques only work for black holes that are actively feeding and glowing brightly in X-rays, which excludes the vast majority of supermassive black holes that are in a quiet state. For every confident spin measurement we see published, there is often a healthy debate within the astrophysics community about the underlying assumptions and potential systematic errors. This means that for most of the spectacular jets we observe, we simply do not have a precise, confirmed measurement of the black hole spin that powers them. We are left inferring the capabilities of the engine by studying the exhaust plume millions of light years away. a fundamental gap in our knowledge that lies at the very core of the jet mystery. At the very foundation of this cosmic engine lies a force that is both invisible and utterly essential: magnetism. We've touched on its role in launching and collimating the jet, but to truly appreciate its power, we need to venture deeper into how these magnetic fields are engineered and maintained. Think of them not just as simple lines on a diagram, but as the fundamental architecture of the entire system. The cosmic power lines that tap directly into the black hole's spin and transform it into a focused, raging beam. This process hinges on a phenomenon of breathtaking elegance and complexity: the twisting of magnetic fields into a tightly wound helix, a structure that acts as both an engine and a guide rail for the jet. The entire sequence begins with the accretion disk. This swirling torus of superheated gas is not just fuel, it's also a dynamo. As the ionized plasma in the disk churns, its motion generates magnetic fields, much like the molten iron in Earth's core generates our planet's magnetic field. But around a black hole, the scales are almost incomprehensibly larger. These nascent fields are then stretched and amplified by the differential rotation of the disk. The fact that material closer to the black hole orbits much faster than material farther out. This stretching process winds the magnetic field lines like a coiled spring, storing immense energy within them. Now enter the black hole's spin. According to the revered Blandford-Zanegic process, the black hole's rotation drags the very fabric of space-time around with it, and if magnetic field lines are anchored in both the accretion disk and the event horizon itself, this spin twists them into an even tighter, more powerful helix. It is this coiled, rotating magnetic structure that acts as a giant slingshot, flinging plasma outward along the polar axis and converting the black hole's rotational energy directly into the jet's kinetic power. This helical model is compelling, but it immediately forces us to confront a monumental puzzle: the problem of magnetic field generation and sustenance. How does a system as chaotic and violent as a black hole's accretion flow create and maintain magnetic fields of such immense, ordered strength over millions of years? The sheer power required is staggering. To confine and accelerate a relativistic jet, the magnetic pressure must be powerful enough to overcome both the intense gravity of the black hole and the turbulent pressure of the infalling plasma. This isn't a minor influence, it's the dominant force in the engine room. The most promising explanation for achieving this is a self-sustaining process known as the magnetorotational instability, or MRI. In essence, the MRI explains how turbulence within the accretion disk can act as a natural amplifier, taking a weak seed magnetic field and stretching and winding it until it grows into a powerful, large-scale ordered structure. It's a virtuous cycle of chaos birthing order, where the very instabilities that drive accretion also work to build the magnetic engine that powers the jet. Yet, even with the MRI, profound questions remain. For the magnetic field to be strong enough to extract the black hole's rotational energy so efficiently, it must be phenomenally concentrated. Some theories suggest this requires a magnetically arrested disk, or a Mayday state, a fascinating and extreme scenario where the external magnetic field becomes so powerful that it actually pushes back against the incoming accretion flow, temporarily halting matter from falling in. In this precarious standoff, the black hole is essentially starved of fuel, but its rotational energy is being tapped with maximum efficiency through the powerful, arrested magnetic fields. It's a paradoxical situation where less accretion leads to a more powerful jet, a concept that challenges our basic intuition about how these systems are fed. Furthermore, the stability of this entire magnetic architecture is a mystery in itself. The helical field is under constant assault. It must resist being torn apart by the sheer forces in the turbulent plasma, avoid dissipating its energy as heat through a process called magnetic reconnection, and remain coherent over distances that span from the event horizon to intergalactic space. How does this delicate, ordered structure survive in such a violent environment? Computer simulations show that these helical fields can be remarkably resilient, creating a self-insulating channel that guides the jet. But they also reveal a constant battle between order and chaos, with magnetic energy building up and being released in violent eruptions. This continuous cycle of construction and destruction might well be the reason we see the bright, flickering knots and shock waves that propagate down the jet, each one a possible testament to a magnetic instability or a reconnection event near the central engine. The magnetic field, therefore, is not a static scaffold but a dynamic, living entity, the true protagonist in the story of the jet, whose origin and enduring strength represent one of the most active and challenging frontiers in theoretical astrophysics. Beyond the immediate spectacle of their raw power, these jets play a role of cosmic architect, shaping the destiny of their host galaxies in a process so profound it touches upon the very cycle of life and death for stars. We now come to a feature that reveals the jet not as a mere bystander, but as a master regulator, its immense impact on galaxy evolution. The mechanism at work here is known as feedback, a deceptively simple term for a process of breathtaking scale and consequence. Imagine a supermassive black hole feasting on surrounding gas, a frenzy of consumption that should lead to the birth of billions of new stars from that very same gas reservoir. Instead, the resulting jet acts as a cosmic circuit breaker, launching a torrent of energy that heats and violently redistributes the galaxy's star-forming fuel, effectively shutting down stellar nurseries for eons. This creates a fascinating and self-limiting cycle. The black hole's own feast triggers a reaction that prevents it from gorging indefinitely, maintaining a delicate balance that governs the growth of both the central monster and the galaxy that cradles it. This feedback operates through several powerful channels. The most direct is straightforward heating. As the jet plows through the vast halo of hot gas that typically surrounds massive galaxies, it injects tremendous energy, raising the temperature of this gas to millions of degrees. When gas is that hot, its particles move so rapidly that the force of gravity from the galaxy itself can no longer pull it together to collapse into new stars. The jet essentially keeps the galactic gas supply in a perpetual, simmering state, preventing it from cooling down and coalescing. It's like turning a stove to high under a pot of water. The water may bubble and steam, but it cannot freeze into ice. In this superheated state, the gas remains diffuse and unavailable for star formation, leading to what astronomers call a red and dead galaxy, a system where no new blue, young stars are born, leaving only an aging population of red stars. But heating is only part of the story. The jet can also enact a more dramatic form of feedback by physically displacing the gas. The intense pressure at the head of the advancing jet can sweep up interstellar material, pushing it out in vast, expanding bubbles that rise through the galactic atmosphere like colossal hot air balloons. In the most extreme cases, this process can drive powerful galactic winds, expelling the gas entirely from the gravitational grasp of the galaxy. This is a transformative, almost apocalyptic event. By removing the primary ingredient for star formation, the jet doesn't just pause the process, it can end it permanently, sentencing the galaxy to a long, slow fade as its existing stars burn out one by one. We see direct evidence for this in galaxies where X-ray observations reveal gigantic cavities, bubbles carved out by the jets in the hot gas surrounding them, silent monuments to past eruptions of incredible power. The profound mystery that researchers grapple with today is not whether feedback happens, but how it happens with such precise efficiency. Why doesn't the feedback either completely obliterate the galaxy or, conversely, prove too weak to have any effect? The system appears to be finely tuned. If the jet were too powerful, it would blow away all the gas, starving the black hole itself of future fuel and preventing the galaxy from ever growing. If it were too weak, the galaxy would continue forming stars unchecked, eventually becoming far larger than the ones we actually observe. The fact that we see a clear correlation between the mass of the central black hole and the mass of the stars in the galaxy's central bulge suggests a long-term, self-regulating relationship has been in place for billions of years. The black hole seems to somehow know how much energy to inject to regulate its host's growth without destroying it. Unraveling the specifics of this self-regulation is a monumental challenge. The efficiency of coupling the jet's energy to the galactic gas is poorly understood. How much of the jet's kinetic energy is converted into heat versus bulk motion? Does the energy dissipate smoothly, or is it delivered in violent, episodic bursts that create a stuttering, stop-start pattern of star formation? The answers likely depend on a myriad of factors, including the jet's power, its composition, the angle at which it strikes the galactic gas, and even the age and mass of the host galaxy itself. Sophisticated computer simulations are our primary tool for studying this cosmic dialogue, and they show that the interplay is incredibly complex, with jets creating turbulence, shock waves, and complex flows that are difficult to model accurately. The long-term effects are even harder to pin down, as we are essentially seeing a single snapshot in a billion-year-long story. This ongoing debate places jet feedback at the heart of modern cosmology, as it is a key process that determines why galaxies look the way they do today, and why the era of rapid star formation in the universe has largely drawn to a close. Moving from the grand scale of galactic evolution, we encounter one of the most personal and pervasive mysteries tied to these jets: their potential role as the primary accelerators for the most energetic particles ever detected, the enigmatic ultra-high-energy cosmic rays. These are not mere specks of dust. They are subatomic bullets, protons, or atomic nuclei carrying as much kinetic energy as a professionally served tennis ball, all compressed into a single, vanishingly small particle. For over a century, these rays have bombarded our atmosphere from the depths of space, their origin one of the longest-standing puzzles in astrophysics. Their incredible energy defies conventional explanation, and black hole jets, with their relativistic fury, stand as one of the few cosmic structures powerful enough to be a credible factory for such extreme particles. The logic for this connection is compellingly straightforward. We know that jets are masters of particle acceleration, capable of whipping electrons to near light speeds, producing the brilliant synchrotron radiation we observe. The same fundamental processes, shock waves and turbulent magnetic fields within the jet should, in theory, be able to operate on a far more powerful scale, accelerating heavier protons and atomic nuclei to the staggering energies recorded. Imagine a natural particle accelerator built on a galactic scale, where a single shock front within the jet could stretch for light years, providing a vast runway for particles to be repeatedly boosted by cascading magnetic waves. This process, known as diffusive shock acceleration, could theoretically push individual protons to energies exceeding 100 million trillion electron volts, placing them squarely in the ultra-high-energy regime. Jets from active galactic nuclei are, in essence, the only celestial objects we know of that possess the combined ingredients for this feat: immense magnetic fields, vast spatial scales, and a relentless supersonic flow. However, moving from a compelling theory to a confirmed source is a monumental detective story, fraught with immense practical challenges. The primary difficulty lies in the nature of the cosmic rays themselves. Unlike photons, which travel in straight lines from their source, cosmic rays are charged particles. This means their paths are hopelessly scrambled by the weak but pervasive magnetic fields that thread the space between galaxies. A proton arriving at Earth from a source 100 million light-years away does not point back to its origin. Its trajectory is a tangled mess, bent and twisted countless times during its journey. It's like trying to trace a single raindrop back to a specific cloud during a hurricane by only looking at the spot where it hit the ground. the directional information is almost entirely lost, leaving us with a sky that appears nearly uniform in its distribution of these ultra-high-energy events. This tracing problem has forced scientists to employ ingenious, indirect methods. One promising avenue is to look for secondary messengers. When an ultra-high-energy cosmic ray collides with a photon from the cosmic microwave background, the faint afterglow of the Big Bang, it can produce a shower of other particles, including neutrinos and gamma-ray photons. Unlike charged protons, neutrinos are ghostly particles that barely interact with matter and travel in perfectly straight lines, while gamma rays are only slightly deflected by magnetic fields. The emerging field of multi-messenger astronomy aims to catch these different signals, a cosmic ray, a neutrino, and a gamma ray, all arriving from the same patch of sky, which would provide a much stronger pointer back to a common source like a flaring black hole jet. A few tantalizing correlations have been suggested, linking neutrino events detected by the Ice Cube Observatory in Antarctica with known blazars, a class of active galaxies whose jets are pointed directly at Earth. These hints are provocative, but the sample size is still too small to be conclusive, and the debate within the scientific community remains fierce. The core of the debate hinges on whether jets are truly efficient enough to be the dominant source. Competing theories point to other extreme phenomena, such as the violent mergers of galaxy clusters or even more exotic processes in the very early universe. Critics of the jet origin theory point out that the highest energy cosmic rays are so powerful that they should lose their energy over intergalactic distances through interactions with background radiation, a limitation known as the GZK cutoff. This implies that the very highest energy particles must come from relatively nearby sources within our local supercluster of galaxies. And here we face another puzzle. When we survey our cosmic neighborhood, we do not see an obvious, powerful jet source that neatly matches the arrival directions of these ultra-energetic events. This either means our understanding of particle propagation is incomplete, that the sources are transient and were only active for a short period in the recent cosmic past, or that we are missing a key piece of the acceleration physics within the jets themselves. The mystery of ultra-high-energy cosmic rays therefore remains a wide-open frontier, with black hole jets as the prime suspect, but a suspect we have not yet been able to definitively place at the scene of the crime. If the steady, colossal power of a black hole jet is a testament to its might, then its sudden, unpredictable flares are a demonstration of its raw, untamed fury. This brings us to a feature that makes these cosmic behemoths feel almost alive, their extreme variability and flaring phenomena. A jet that has shone with a consistent brilliance for decades can, without any warning, erupt into a flash of light that outshines its entire host galaxy, only to fade back to its normal state just as rapidly. These are not subtle flickers. We're talking about changes in brightness by factors of 10 or even 100, playing out on timescales that range from mere minutes to several years. This wild behavior is far from a simple light show. It is a frantic, encoded message from the very heart of the engine, a message we are still struggling to fully decipher. The first crucial clue hidden in these flares is their incredible speed. When a jet doubles its brightness in just a few hours or days, it imposes a strict limit on the size of the region responsible for the outburst. This is a fundamental principle of physics. A source of light cannot vary faster than the time it takes light to travel across it. A flash that occurs over 24 hours, for instance, must be generated in a region smaller than 24 light hours across. To put that in perspective, that's an area smaller than the orbit of Pluto around our Sun. The staggering implication is that these titanic explosions of energy, capable of outshining billions of stars, are being generated in a volume of space that is, by cosmic standards, extraordinarily compact. This forces the origin of the flares deep into the jet's base, terrifyingly close to the black hole itself, where conditions are most extreme and energies are at their peak. So, what could possibly cause such a violent and rapid release of energy in such a confined space? Astrophysicists have two primary suspects, and it's likely that both are at play in different systems or at different times. The first suspect is the accretion disk. Picture this disk not as a smooth, placid river of gas, but as a seething, chaotic cauldron. Instabilities are inevitable. A dense clump of material might break away from the inner edge of the disk and plunge suddenly into the black hole. Alternatively, magnetic stresses could build up within the disk until they snap, releasing a torrent of energy, much like the sudden slippage of a tectonic plate causes an earthquake. This sudden injection of extra fuel, this gravitational gulp, would send a powerful shock wave racing down the nascent jet. This shock wave would then act like a colossal piston, compressing the plasma and magnetic fields within the jet, and in the process, accelerating particles to even higher energies, causing that specific segment of the jet to blaze with intense new light. The second, and perhaps even more compelling suspect, is a dramatic event happening within the jet's own magnetic architecture, magnetic reconnection. Remember those powerful, twisted magnetic field lines that are crucial for launching and confining the jet? They can become so tightly wound and stressed that they literally snap and reconfigure themselves into a lower energy state. Think of it as a colossal, cosmic short circuit. When two oppositely oriented magnetic field lines are forced together, they can break and reconnect, releasing a tremendous amount of stored magnetic energy in an explosive burst. This process directly heats the plasma and creates strong electric fields that are incredibly efficient at accelerating particles to near light speed almost instantaneously. Magnetic reconnection is a prime candidate for explaining the very fastest flares, the ones that appear to turn on and off in a matter of minutes, because it can dump immense energy into a very small volume over a very short time, creating a brilliant, localized flash right in the jet's core. The true challenge and the core of the mystery is that we often cannot tell which of these two processes, an accretion disk instability or a magnetic reconnection event, is responsible for any given flare we observe from Earth. The light that reaches our telescopes is a blended signal, a composite of the entire jet's emission. A flare caused by a new shock wave from the black hole might look very similar to one caused by a reconnection event happening further down the jet. To make matters more complex, these phenomena can be linked. A surge of matter from the disk could destabilize the magnetic field in the jet, triggering a reconnection event, creating a cascade of effects that is nearly impossible to untangle. This is why predicting this flaring behavior is one of the most difficult tasks in all of high-energy astrophysics. The system is fundamentally chaotic, a non-linear engine where a small perturbation at the center can lead to a wildly disproportionate eruption downstream. This inherent unpredictability transforms our study of these jets from a simple act of observation into a form of cosmic seismology. We are monitoring the equivalent of celestial earthquake zones, waiting for the next big one to hit. Each major flare is a unique opportunity, a fleeting moment when the inner workings of the engine are briefly illuminated. By analyzing the exact spectrum of light emitted during a flare, how its brightness changes across different wavelengths from radio to gamma rays, and by measuring the polarization of that light, which tells us about the structure of the magnetic fields, we can slowly piece together the physical conditions in the eruption zone. Some of the most exciting discoveries in recent years have come from coordinated worldwide campaigns, where telescopes all across the globe and in space swivel to stare at a single flaring blazar, capturing its tantrum across the entire electromagnetic spectrum in real time. These frantic observing sessions are our best hope for finally isolating the trigger, allowing us to move from simply watching the fireworks to truly understanding the fuse. After traversing millions of light years, the jet's epic journey must eventually come to a violent and spectacular end. This final confrontation occurs when the relentless, narrow beam of plasma slams into the tenuous gas that pervades the space between galaxies, the intergalactic medium. The result is not a simple, quiet dissipation, but a cosmic train wreck in slow motion, a collision of unimaginable force that gives birth to some of the largest structures in the universe, gigantic radio-bright lobes. These are the celestial footprints of the jet's immense power, vast balloons of magnetized plasma that can dwarf the host galaxy itself, often spanning hundreds of thousands of light years across. The boundary where this dramatic transformation occurs is known as the termination shock, a pivotal and fiercely energetic region where the ordered, fast-flowing jet suddenly decelerates and splatters its contents into a much broader reservoir. The physics of this terminal shock is both brutal and beautiful. Picture a supersonic jet encountering a wall, not a solid wall, but a diffuse, gaseous one. The jet's material, still moving at a significant fraction of light speed, cannot simply push this gas aside gently. Instead, it piles up on itself, creating a massive shock front where its kinetic energy is abruptly converted into turbulence, heat, and radiation. This is the termination shock, a cosmic equivalent of a sonic boom, but on a scale that defies human comprehension. It's at this chaotic interface that the jet's particles receive one final, tremendous boost. The shock wave acts as a natural and enormously powerful particle accelerator, even more effective than the processes near the black hole in some ways. Charged particles can bounce back and forth across this magnetic barrier, trapped by the turbulence, gaining a little more energy with each crossing until they are flung away with monstrous intensity. This process is responsible for making these lobes brilliant beacons in the radio sky, as the ultra-energetic electrons spiral through the lobe's magnetic fields, emitting synchrotron radiation that we can detect across the universe. Yet for all the apparent simplicity of this model, the structures we observe are anything but uniform. We see a stunning variety of forms in these giant radio lobes. Some appear as smooth, classic balloons, suggesting a relatively steady and stable flow from the central engine over millions of years. Others are riddled with intricate filamentary structures, swirls, and edges that look strangely sharp, as if the plasma is being confined or shaped by unseen forces. Some lobes even appear to be detached from their host galaxy entirely, floating in space like ghostly relics of a past eruption, while others are connected by a faint bridge or plume of material back to the central source. This incredible diversity presents a major puzzle. If the basic physics of the termination shock is the same, why do the resulting structures vary so dramatically from one system to another? The answer likely lies in the complex and dynamic interplay between the jet and its environment. The intergalactic medium is not a uniform sea. It is lumpy, filled with wisps of older galactic gas, dark matter halos, and the tenuous filaments of the cosmic web. A jet plowing into a dense cloud will have its progress slowed, its lobe distorted into a peculiar shape, while a jet flowing into a near vacuum might create a much more symmetrical, expansive structure. Furthermore, the jet itself may not be a steady fire hose. It could be episodic, turning on and off over tens of thousands of years. In this scenario, a new, young jet can sometimes re-energize an old, faded lobe from a previous active phase, creating a complex, nested structure that tells a layered history of the black hole's outburst. The magnetic fields within the lobes add another layer of mystery. They should naturally decay and dissipate over time, yet the sharp edges and bright filaments we see suggest that these fields are being somehow restructured and amplified long after the material has passed through the initial shock, possibly through ongoing turbulence or secondary shocks within the lobe itself. Perhaps the most profound question concerns the ultimate fate of the energy the lobe contains. These vast reservoirs are not just glowing clouds, they are stored energy on a galactic scale. This energy can heat the surrounding intergalactic gas, preventing it from cooling and falling back into the galaxy to form new stars, a crucial form of feedback we discussed earlier. However, the efficiency of this heating is highly uncertain. Does the lobe's energy dissipate smoothly and gently like a radiator warming a room? Or does it leak out in violent, localized bursts? The complex, finger-like structures and turbulent edges seen in many lobes suggest that the energy may not be transferred uniformly, but might instead create hotspots and cavities that stir the intergalactic medium in a much more chaotic and unpredictable fashion. Understanding this energy transfer is vital because it determines how a single black hole, through its jet and lobes, can dictate the climate for an entire galaxy cluster, influencing the birth and death of stars for hundreds of millions of years. The termination shock and its resulting lobes are therefore not an end, but a transformation, a place where the focused fury of the jet is finally released to sculpt the cosmos on its very largest scales. This stark disparity leads us directly to one of the most perplexing questions at the heart of jet physics. Why are some supermassive black holes brilliant cosmic lighthouses, while others, seemingly just as well fed, remain shrouded in darkness? It's a fundamental puzzle of cosmic engineering. We observe galaxies with virtually identical black hole masses and ample reservoirs of surrounding gas, yet one will launch a jet that sculpts its environment for millions of light years, and its neighbor will be utterly quiescent. This tells us that the mere presence of fuel and a massive gravitational engine is not enough. There is a hidden switch that must be flipped to activate this incredible phenomenon, and identifying that switch remains a primary goal for astronomers. The most compelling candidate for this switch is the black hole spin. Think of it as the difference between a battery that is fully charged and one that is completely drained. A non-spinning or slowly spinning black hole is like a dead battery. It has immense mass and gravity, but it lacks the rotational energy that theoretical models like the Blandford-Zienagic process require to power the jet. A rapidly spinning black hole, however, is a fully charged cosmic battery, its rotation twisting space-time and magnetic fields into the precise configuration needed to launch a relativistic beam. This idea elegantly explains why two black holes of the same mass could behave so differently. One may have been spun up by a consistent, ordered flow of accreting material over eons, while the other might have received chaotic, random infalls of matter that cancelled out its spin, leaving it dormant. The challenge, as we've discussed, is that directly measuring spin is notoriously difficult, leaving this elegant theory in need of more conclusive evidence. But spin alone may not be the whole story. The way a black hole eats appears to be just as important as how fast it's spinning. This brings us to the critical concept of accretion mode. Picture two different ways you could feed a fire. You could carefully place dry, seasoned logs onto the flames in a structured, orderly manner, creating a strong, stable blaze. Alternatively, you could haphazardly dump a pile of wet, green wood and leaves onto it, which would likely smother the flames, creating a great deal of smoke and sputtering, but no sustained, powerful fire. In many ways, black holes experience a similar dichotomy in how they consume matter. The stable, efficient feeding mode is often compared to a well-organized rotating disk, a so-called thin disk where gas spirals inward in a smooth, predictable fashion. This ordered flow seems to be conducive to generating and sustaining the large-scale, powerful magnetic fields needed for jet production. It's the equivalent of feeding the fire with dry logs. The other mode, known as a radiatively inefficient or advection-dominated flow, is far more chaotic. Here, the infalling gas is so hot and diffused that it doesn't cool efficiently. It's a puffy, turbulent cloud rather than a neat disk. In this messier state, the accretion is Chinese letter a chaotic downpour than a steady stream, and this turbulence may prevent the magnetic fields from organizing themselves into the tight, helical structure required to launch a jet. The black hole is still feeding, but it's eating in a way that simply cannot power the engine, effectively keeping the switch in the off position. The transition between these two accretion states likely depends on the rate of fuel supply, and this may explain why some active black holes flicker on and off over cosmic time. The final piece of this puzzle brings us back to the invisible architecture of magnetism. Even with rapid spin and an orderly accretion disk, a jet might still fail to form if the magnetic field is not configured in just the right way. The field needs to be both incredibly strong and possess a specific, large-scale order. If the magnetic field near the black hole is too weak, it simply doesn't have the grip to extract rotational energy. If it's too tangled and disordered, a chaotic mess of small loops, it cannot act as the coherent slingshot needed to fling material outward in a narrow beam. The switch might only flip to on when a sufficient amount of magnetic flux, a measure of the field's strength and coherence, is delivered to the immediate vicinity of the event horizon. This concept, known as the magnetically arrested disk or MAD state, represents a kind of magnetic perfection where the external field is so strong it temporarily chokes off the accretion flow, creating a standoff that allows for maximum energy extraction. The open question is what conditions in the galaxy and its central black hole allow for the buildup of such an ideal magnetic configuration, and why some systems achieve this state while others do not. The true mystery is that these three factors, spin, accretion mode, and magnetic field configuration, are undoubtedly intertwined in a complex feedback loop that we are only beginning to map. A change in one likely influences the others. A switch in accretion mode could alter the magnetic field structure, which in turn could affect how efficiently the black hole's spin is tapped. This intricate dance makes it nearly impossible to point to a single, universal trigger. It suggests that the on/off switch for black hole jets is not a simple button, but a complex combination lock, with the precise code varying from one galactic core to another. Solving this requires us to move beyond studying these beasts in isolation and to begin understanding the full life history of a supermassive black hole, its past mergers, its diet over billions of years, and the dynamic environment of its host galaxy, all of which may hold the ultimate key to why some darkness remains silent while other darkness roars. Light from these cosmic jets carries more than just raw intensity. It holds a subtle, hidden signature that can reveal the deepest secrets of their internal structure. This signature is known as polarization, a property that describes the preferred direction in which the light's electric field vibrates. For light emitted by the fast-moving electrons in a jet, a process called synchrotron radiation, the polarization acts like a cosmic compass, directly tracing the orientation of the magnetic fields that guide those electrons along their path. When we measure this light and find it is highly polarized, with the electric fields all vibrating in the same plane, it tells us that the magnetic fields at that location are remarkably smooth and ordered, like a vast bundle of perfectly aligned fibers. A tangled, chaotic magnetic field would produce unpolarized light, a jumbled mess of different vibrational directions. So, by carefully analyzing the polarization of a jet, we can effectively map the invisible architecture of its magnetic skeleton across millions of light years. This powerful diagnostic tool has delivered a series of stunning and often baffling revelations. In many jets, we observe a high degree of polarization that remains remarkably stable over long stretches, indicating the presence of a strong, large-scale magnetic field that is incredibly resilient against the turbulent forces within the plasma flow. These fields often appear to be aligned parallel to the jet's axis, forming a tight, straitjacketing sheath that helps maintain its legendary collimation. This is precisely what many of our leading models predict, a well-ordered helical field that provides both the launch mechanism and the long-range stability. However, the universe is rarely so tidy, and the polarization data frequently deviate from this clean picture in ways that are deeply puzzling. One of the most persistent mysteries arises when we map the polarization angle, the specific direction of the electric field vibration along the length of a jet. Instead of remaining uniformly aligned, we often see the polarization angle suddenly rotate or even form a distinct swirling pattern. In some cases, the magnetic field seems to twist around the jet's core like a corkscrew, a direct signature of that helical magnetic structure we've theorized about. Yet the sheer scale and coherence of these twists can be difficult to reconcile with a turbulent plasma flow. How does this delicate magnetic helix survive for such vast distances without being shredded apart by internal instabilities? Other times, the polarization angle makes an abrupt 90-degree shift, suggesting the magnetic field transitions from being parallel to the jet to being perpendicular to it. This could mark the location of a powerful shock wave within the flow, where the plasma is suddenly compressed and the magnetic field is squeezed and reoriented. But why do we see these sharp transitions in some jets and not in others? The patterns are inconsistent, suggesting that the internal dynamics of jets are far more complex and varied than any single model can currently encompass. Perhaps the most dramatic polarization puzzles come from observations of flaring jets, particularly blazars whose beams are pointed right at us. During a major outburst, astronomers have witnessed the polarization angle undergo wild, rapid swings, sometimes rotating through hundreds of degrees over just a few days. This is behavior that is incredibly difficult to explain. One compelling idea is that we are witnessing a knot of plasma, a bright shock front, traveling along a spiral path within a curved magnetic field. As this knot moves, our viewing angle to its local magnetic field changes, making the polarization angle appear to rotate. Another, more exotic possibility is that the flare itself is caused by a massive magnetic reconnection event, a cosmic short circuit where the field lines break and reconnect in a new configuration. As the reconnection site evolves, the dominant magnetic field direction in the emission region could be rapidly shifting, causing the observed polarization to dance erratically. These events put our models to the ultimate test because they imply that the magnetic fields at the very heart of the jet are not static scaffolds, but are instead dynamic and explosive, capable of global reconfiguration in a matter of days. The profound challenge these observations present is a direct confrontation between order and chaos. The very existence of high polarization demands a high degree of magnetic order, yet the sudden changes in that order suggest a system that is fundamentally unstable or prone to violent reorganizations. Our simulations struggle to recreate this delicate balance. They often produce fields that are either too ordered and rigid, unable to explain the rapid swings, or too chaotic and turbulent, unable to produce the high degrees of polarization we consistently observe. This polarization puzzle therefore strikes at the very heart of our understanding of jet physics. It forces us to ask whether the magnetic field is a stable, external guide for the jet, or if it is an emergent property of the flowing plasma itself, constantly being generated and destroyed by internal turbulence. Each new polarization map we obtain is like getting a glimpse of the jet's nervous system, and the signals we're receiving reveal a beast that is both beautifully structured and fundamentally volatile. Its inner magnetic life far more complex and unpredictable than we ever imagined. Beyond the brilliant glow of radio waves and X-rays, some black hole jets unleash an even more extreme form of radiation, pushing the boundaries of energy itself. This is the realm of tera-electronvolt gamma rays, a form of light so energetic that a single photon carries 1 trillion times more energy than a particle of visible light. Detecting these TV photons is like finding the cosmic equivalent of a cannonball mixed in with a shower of raindrops. It signals that truly extraordinary and violent processes are at work within the jet. The fact that we can detect them at all from sources billions of light years away is a miracle of physics and a profound puzzle, because the very environment that creates these gamma rays should, in theory, also be perfectly equipped to destroy them before they can ever escape. The leading mechanism for producing such insane photon energies is a spectacular two-step dance known as inverse Compton scattering. To understand this, we first need to recall that the jet is already filled with lower energy photons, the synchrotron radiation produced by electrons spiraling at near light speed. Now imagine one of these relativistic electrons, a particle carrying enormous kinetic energy, on a collision course with a low-energy synchrotron photon. In a normal collision, a more energetic photon would impart energy to a less energetic electron. But here, the roles are reversed due to the electron's incredible speed. In a process akin to a ping-pong ball being slammed by a professional tennis racket, the ultra-fast electron transfers a massive amount of its own kinetic energy to the photon. This single interaction can boost the humble synchrotron photon into a monstrous TV gamma ray, effectively converting the jet's particle energy directly into the highest energy light in the universe. However, this brilliant solution immediately creates an even bigger mystery known as the absorption problem. The jet is absolutely flooded with these same lower energy synchrotron photons. A newly minted TV gamma ray on its journey to escape the jet faces a high probability of colliding with one of them. When a TV gamma ray meets a lower energy photon, they can annihilate each other, producing an electron and a positron pair in a process fittingly called pair production. This is the great cosmic irony. The very population of synchrotron photons that provides the raw material for creating TV gamma rays through inverse Compton scattering also forms a thick fog that should absorb and eliminate those same gamma rays before we can ever see them. For many standard jet models, the inner, most luminous regions should be completely opaque to TV radiation, making their detection from Earth seemingly impossible. The fact that we do detect brilliant and variable TV flares from many blazars means our understanding of the jet's internal structure is incomplete. These observations force us to reconsider the geometry and location of the gamma ray factory. One compelling idea is that the TV emission does not originate from deep within the opaque core of the jet, but from a much larger, more diffuse region further out. In this scenario, the shock waves that accelerate particles are spread across a vast volume, diluting the density of the target synchrotron photons. With fewer photons to collide with, the TV gamma rays have a clear path to escape, solving the absorption problem at a stroke. This would be like moving a factory from a cramped, crowded room to an open field. The same production can happen, but the products can leave freely. Another fascinating possibility involves a highly stratified or structured jet. Perhaps the jet possesses a fast, narrow spine surrounded by a slower, denser sheath. The inverse Compton scattering could occur primarily in the sparse spine, where the target photon density is low, while the brighter synchrotron emission comes mainly from the denser sheath. Alternatively, the jet might be segmented with compact, powerful accelerators separated by large, relatively empty gaps. There is also the provocative theory of ultra-relativistic boosting. If the region producing the gamma rays is moving toward us at a speed even closer to the speed of light than the rest of the jet, the effects of special relativity come into play. This extreme boosting could shift the entire emission to higher energies in our frame of reference while simultaneously making the region appear more compact and less dense with target photons, somehow evading the absorption threshold. The rapid variability of these TV flares adds yet another layer of complexity. When a jet doubles its TV brightness in a matter of minutes, it once again points to an incredibly compact emission region, right back in the zone where absorption should be strongest. This creates a direct tension between the small size implied by the quick variations and the large size needed to avoid absorption. Reconciling this forces theorists to consider truly exotic models, including the possibility of specific magnetic field configurations that naturally create low photon density cavities, or scenarios where the gamma rays are produced in a relativistic blast wave that is itself optically thin. Each new observation of TV gamma rays, therefore, is not just a data point. It is a stringent test of our most fundamental ideas about the jet's interior, pushing us to imagine more intricate and dynamic designs for these cosmic particle accelerators. But what if we could shrink this entire cosmic drama down to a manageable scale, bringing it into our own galactic backyard for closer inspection? This brings us to a fascinating and powerful tool in the astrophysicist's toolkit, the microquasar. Imagine taking the colossal engine of a supermassive black hole and its brilliant jets and compressing it into a system small enough to orbit a single star right here in the Milky Way. That is precisely what a microquasar is: a stellar mass black hole or neutron star, often in a binary pair with a normal star, that is actively feeding and, in the process, launching its own tiny but incredibly powerful relativistic jets. These systems are not merely curiosities. They are our most valuable local laboratories for studying jet physics in real time, offering a unique window into processes that would otherwise be impossible to resolve in distant quasars billions of light years away. The greatest advantage microquasars provide is the gift of time. The physics governing the launch and propagation of a jet operates on a timescale that is intrinsically linked to the size of the central engine. A supermassive black hole with an event horizon that could engulf our entire solar system operates on a stately cosmic clock. Changes in its accretion disk or jet can unfold over centuries or millennia. But a stellar mass black hole with an event horizon merely tens of kilometers across is a frantic, high-speed machine. The same physical processes: accretion disk instabilities, magnetic reconnection events, and jet launching can play out in a matter of hours, days, or weeks. We can literally sit and watch an entire outburst cycle from start to finish. A microquasar can flicker on, launch a new set of jets, flare dramatically, and then fade back into quiescence, all within a single observing season. This allows us to directly witness the cause and effect relationships that are only inferred from a single, frozen snapshot of a distant supermassive system. We can see how a sudden influx of material from the companion star triggers a change in the jet's power, or how a flaring event in X-rays correlates with the ejection of a new, bright knot of plasma down the jet, providing an unprecedented level of detail on the intimate connection between accretion and ejection. Furthermore, the concept of scaling laws provides a powerful theoretical bridge between these small and large systems. The underlying physics of gravity, magnetohydrodynamics, and particle acceleration are believed to be universal. This means that the fundamental equations that describe how a jet is formed and powered can be scaled from a stellar mass black hole to a supermassive one, with the primary variable being the mass of the central object. If you know how a process behaves in a microquasar, you can, in principle, scale it up by a factor of millions to predict how it should behave in a quasar. This scaling has been remarkably successful in explaining broad similarities, such as the basic spectral states of accretion and the correlation between jet power and accretion rate. It confirms that we are indeed looking at the same fundamental beast, just wearing a different sized coat. However, just when this elegant picture seems complete, the universe reveals critical and puzzling differences that prevent a simple, direct application of microquasar knowledge to their supermassive cousins. The environment surrounding these two classes of objects is profoundly different, and this environment plays a crucial role in shaping the jet's destiny. A microquasar jet propagates through the dense and complex circumstellar environment of its own binary system. It must plow through stellar winds from its companion star, navigate through remnants of previous outbursts, and interact with the interstellar medium of our galaxy. This often leads to jets that are bent, disrupted, or that create bright, localized shock fronts as they collide with these obstacles. In contrast, a supermassive black hole jet emerges into the relatively pristine and tenuous halo of its host galaxy and then into the intergalactic void. This vast difference in external pressure and density can drastically alter the jet's stability, collimation, and long-term evolution, meaning that while the launch mechanism may be scalable, the subsequent journey is not. An even more fundamental discrepancy may lie in the very diet of the black hole. A supermassive black hole typically feeds from a large, massive, and relatively stable accretion disk that can persist for millions of years. A microquasar, however, often accretes matter in a more violent and unstable manner, such as through a torrential stream of gas ripped directly from the surface of its companion star. This difference in accretion mode could lead to significant variations in the strength and configuration of the magnetic fields that are crucial for jet formation. The magnetic field in a microquasar might be more turbulent and disordered, while that around a supermassive black hole could have time to organize into the large-scale, stable structures needed for a persistent, highly collimated jet. This suggests that the on/off switch for jets and their resulting properties may be sensitive not just to the mass of the black hole, but to the specific and often messy details of how it is being fed. The microquasar analogy, therefore, is not a perfect one-to-one mapping, but rather a vital and humbling guide. It provides the crucial short-term, high-resolution data we desperately need, while simultaneously teaching us that the full story of cosmic jets requires an appreciation for the unique and complex life history of each individual system, from the smallest stellar remnant to the most colossal giant at the center of a galaxy. But for all the talk of black hole spin and magnetic fields, there is a third, equally vital character in this cosmic drama, the swirling, tempestuous feast that fuels the entire system, the accretion disk. The relationship between this disk of infalling material and the jet it helps spawn is one of profound complexity and mutual influence. It is not a simple one-way street where the disk passively provides fuel and the jet simply ignites. Instead, they are locked in a dynamic, often turbulent dance, where the state and stability of the disk appear to act as a master regulator, a kind of cosmic throttle that can either unleash a relativistic beam or keep the engine in a quiet, smoldering state. This intricate connection is clearly observed, yet its underlying theoretical principles remain one of the most active and challenging frontiers in astrophysics. To grasp this relationship, we must first appreciate that not all accretion disks are created equal. They can exist in dramatically different states akin to the different phases of matter, and the specific state of the disk seems to be the primary determinant of whether a powerful, persistent jet is launched. On one end of the spectrum, we have the classic geometrically thin and optically thick disk. Picture a vast, serene whirlpool of gas orbiting the black hole in a smooth, orderly fashion. As the gas spirals inward, it rubs against itself through a process called viscosity, heating up through friction and glowing brilliantly across the electromagnetic spectrum, from ultraviolet to soft X-rays. This is a stable, efficient, and radiant mode of accretion. For a long time, it was assumed that this was the ideal state for jet production, a well-fed engine running on high-quality fuel. However, observations have painted a more nuanced picture. While these thin disks are often associated with bright quasars and active galaxies, the production of a large-scale, relativistic jet in this state is not guaranteed and may require the additional, perfect conditions of high black hole spin and a strong, ordered magnetic field to truly activate. On the opposite end of the spectrum lies a radically different state, the hot, radiatively inefficient accretion flow. Imagine replacing that serene whirlpool with a puffy, bloated, and turbulent cloud of plasma. In this state, the gas is so hot and diffuse that it cannot cool down efficiently by radiating away its energy. Instead of losing energy and spiraling inward in a neat, compact disk, the infalling material essentially carries its thermal energy with it, a process known as advection. The result is a thick, spherical-like torus of seething plasma that is much less luminous for the amount of mass it is accreting. For decades, it was thought that these hot, inefficient flows were jet-suppressed, as their turbulence and lack of a well-ordered structure seemed inimical to forming the large-scale magnetic fields needed for launching. Yet, to the great surprise of theorists, some of the most powerful and persistent jets we observe, particularly from low-luminosity active galactic nuclei and certain X-ray binary systems, are unequivocally associated with this very state. It's a profound paradox. A seemingly chaotic and inefficient way of feeding a black hole appears to be remarkably effective at powering its jet. This paradox has led to a revolutionary shift in thinking. The key may lie not in the disk's luminosity or its neatness, but in its ability to create and sustain a specific magnetic environment. A hot, thick accretion flow, despite its turbulence, has two potentially jet-friendly properties. First, its low density and high temperature mean that the magnetic pressure can become a dominant force, potentially overwhelming the thermal pressure of the gas. This allows the magnetic fields to organize into a more powerful, large-scale structure. Second, and more specifically, this state is thought to be a prerequisite for achieving the coveted magnetically arrested disk or MIDI regime we discussed earlier. In this extreme scenario, the external magnetic field dragged in by the accretion flow becomes so strong that it actually pushes back against the incoming matter, arresting its flow near the event horizon. This creates a standoff, a bottleneck of magnetic energy that is then tapped with incredible efficiency by the black hole's spin via the Blandford-Zeenagic process. In this counterintuitive framework, the jet is not powered by the kinetic energy of the accreting gas itself, but by the black hole's spin, with the arrested magnetic field acting as the perfect intermediary. The inefficient, puffy disk, therefore, isn't a mess, it's a perfect magnetic battery charger. The practical evidence for this disk-jet coupling is vividly demonstrated by the behavior of microquasars in our own galaxy. We can watch in real time as a stellar mass black hole transitions between different accretion states, and with stunning regularity, the appearance and disappearance of its radio jet follows a predictable pattern. When the system is in a bright, high-energy state dominated by the thermal emission of a thin disk, the steady jet is often quenched. Then, as the accretion rate drops and the system makes a transition into a harder, more dominated state characterized by a hot corona or a thick flow, a powerful, relativistic jet is often launched and detected in the radio band. This correlation is so robust that it has been enshrined as a fundamental empirical law in the study of black hole systems. It tells us that the jet is not simply a function of how much the black hole is eating, but how it is eating. The switch to turn on the jet seems to be thrown precisely when the accretion flow undergoes a fundamental state transition, reorganizing the magnetic architecture at the heart of the engine. The profound mystery that remains is understanding the exact microphysics that governs this transition. What specific instability or threshold in the disk's density, temperature, or magnetic flux triggers the shift from a jet-less to a jet-launching configuration? Why does a fainter, seemingly struggling disk sometimes produce a more powerful jet than a brilliantly shining one? Our computer simulations are only beginning to capture the full complexity of this process, needing to model the general relativity of the black hole, the magnetohydrodynamics of the plasma, and the radiative transfer of energy simultaneously. The answers are critical because they would provide a unified theory of black hole accretion and ejection, explaining not just the brilliant beacons of the distant cosmos, but also the quiet, jet-producing giants lurking at the centers of nearby galaxies like our own Milky Way. The accretion disk, therefore, is far more than a simple fuel tank. It is the intelligent control system of the entire cosmic engine, its internal state holding the final key to understanding why and when darkness decides to scream. Yet another layer of complexity in the behavior of these jets emerges when we observe them not as static, rigid structures, but as dynamic beams that appear to sway, wiggle, and even corkscrew through space over time. This phenomenon, known as jet precession, is like watching a celestial garden sprinkler on a cosmic scale, where the entire jet slowly changes its direction of pointing, tracing out a cone-like pattern in the sky. In some dramatic cases, we can actually see the jet's path not as a straight line, but as a distinct helical or sine wave pattern etched across thousands of light years, a fossil record of a persistent wobble that has been ongoing for millions of years. This precession isn't a mere curiosity. It is a direct tracer of the dynamic and often unstable environment at the very heart of the black hole system, offering us a unique, if challenging, way to probe the physics of the central engine. The search for the cause of this wobbling leads us directly back to the black hole's spin, and a fascinating prediction of Einstein's theory of general relativity called frame dragging, or the lens-thirring effect. The idea is that a spinning black hole doesn't just create a gravitational well, it also drags the very fabric of space-time around with it, like a spinning bowling ball submerged in a thick fluid. This dragging effect creates a kind of gravitational vortex that exerts a torque on any surrounding object, most notably the inner regions of the accretion disk. If the disk is not perfectly aligned with the black hole's equatorial plane, this frame dragging force will cause the inner part of the disk to precess, meaning its axis of rotation will slowly wobble around that of the black hole. Since the jet is launched perpendicular to the inner disk, this wobble is then imprinted directly onto the jet itself. It's a beautifully elegant concept. The jet's grand, sweeping motion across the cosmos is a direct, amplified reflection of the subtle warping of space-time right at the event horizon. However, the accretion disk itself can be the source of the wobble without any help from frame dragging. Disks are not always stable, flat platters. They can become warped. This can happen through a variety of mechanisms. If the black hole is in a binary system, the gravitational pull of its companion star can torque the disk. Alternatively, if the infalling gas arrives from multiple directions or with misaligned angular momentum, it can strike the disk and cause it to tilt. A warped disk will naturally precess as it orbits, and just like with the lens-thirring scenario, this precession is communicated to the jet, causing it to wobble in sync. The challenge for astrophysicists is that from our distant vantage point, the observable consequence, a precessing jet, can look remarkably similar, whether it's being driven by the subtle twist of space-time from a spinning black hole or by the more classical gravitational torques from a warped disk. Disentangling these two primary causes is a monumental task with our current observational capabilities. The period of the precession, the time it takes for the jet to complete one full wobble, holds a key clue. Precession driven by the lens-thirring effect is expected to be relatively rapid, occurring on timescales of days to years for stellar mass black holes in microquasars, and potentially thousands of years for supermassive black holes. Precession from a warped disk, on the other hand, can operate on a wide range of timescales, from very short to extremely long, depending on the specific cause of the warp. To make a definitive distinction, we would need incredibly precise, long-term monitoring of the jet's motion coupled with independent measurements of the black hole's spin and the orientation of its accretion disk, a set of data that is exceptionally difficult to obtain for any single system, let alone for the many precessing jets we see across the universe. This leaves us in a tantalizing position. The observed precession of jets is a powerful, visible testament to the dynamic dance between a black hole's spin, its accretion disk, and the very geometry of space itself. Yet, for nearly every precessing jet we study, the precise driver of the wobble remains an open question. It is entirely possible that both mechanisms are at work simultaneously in many systems, with their effects intertwined, creating a complex precession pattern that is difficult to decode. Solving this mystery is crucial because the precise nature of the wobble encodes fundamental information about the black hole's spin and the stability of its feeding process. Each processing jet is like a cosmic gyroscope, and learning to read its motion correctly will allow us to peer even deeper into the hidden heart of the most powerful engines in the universe. Just when we think we've grasped the jet as a continuous beam, our telescopes reveal it is often anything but. In many of the most spectacular jets, we see them not as smooth rivers of light, but as strings of brilliant pearls, a series of distinct glowing knots or bubbles, often spaced with a surprising and unsettling regularity. These are not random clumps. They appear almost like a cosmic harmonic, a set of sound waves frozen in plasma and light propagating down the jet's length. These regularly spaced structures are one of the most visually striking and theoretically challenging features we observe, because they point to a powerful, repeating process at the black hole's heart, a kind of cosmic drumbeat whose rhythm we can see but whose source we cannot yet fully hear. The most intuitive explanation for these patterns lies in the idea of shocks. Picture the jet not as a perfectly steady flow, but as a river with a variable current. If the black hole's engine experiences a sudden surge in power, a gulp of extra matter from the accretion disk, or a violent magnetic reconnection event, it can send a pulse of higher pressure plasma racing down the jet. This faster-moving material eventually catches up with the slower, previously ejected plasma ahead of it. When they collide, the interaction isn't gentle. It creates a shock front, a sharp discontinuity where the plasma is suddenly compressed, heated, and its particles are accelerated to even higher energies. This shock region then glows brilliantly, appearing to us as a bright knot. If the central engine is pulsating, sending out such surges at regular intervals, then a series of these shocks will form, creating that observed chain of evenly spaced knots, each one a fossilized echo of a past eruption from the galactic core. This concept of a pulsating engine leads to a fascinating and almost musical analogy. The jet may be acting like a gigantic wind instrument. In an organ pipe or a flute, a column of air vibrates at specific resonant frequencies, creating standing waves with nodes and antinodes at fixed positions. Some theorists propose that the entire cavity where the jet is launched, the region between the black hole and the inner edge of the accretion disk, could act as a similar resonant chamber. Here, the sound waves are not vibrations in air, but powerful magnetohydrodynamic waves, oscillations in the density and magnetic pressure of the plasma itself. A disturbance in this cavity could set up a standing wave pattern, causing the jet's power output to rhythmically increase and decrease. Each peak in this cycle would launch a new blob of energetic plasma, creating the periodic knots we observe downstream. It's a profoundly elegant idea, suggesting that the largest structures in the universe can be governed by the same principles of wave mechanics as the smallest. Yet for all the elegance of this shock and resonance model, the universe, as always, refuses to conform to our neatest theories. The primary mystery arises when we carefully measure the spacing and evolution of these knots over time. In a simple, steady flow, the distance between these shock-formed knots should steadily increase as they travel outward. The first knot ejected has a head start, but the one behind it is launched into a clearer channel and might travel slightly faster, so the gap between them should widen predictably over thousands of years. While we do see this in some systems, in many others, the knots remain stubbornly evenly spaced, or even show patterns that defy this simple ballistic motion. Some knots appear to brighten and then fade not in sequence, but almost simultaneously, as if an invisible wave of energy is passing through them. Others show evidence of merging or interacting in ways that suggest the jet's internal environment is far more complex than a simple vacuum through which blobs travel. This discrepancy forces us to consider that the knots might not be independent blobs at all, but rather part of a continuous, underlying wave structure within the jet itself. Instead of being discrete bullets of plasma, they could be manifestations of a true propagating wave, specifically a reconfinement shock. Imagine the jet, as it travels outwards, begins to expand under its own pressure. But the external medium, the intergalactic gas, exerts a constant confining pressure. At a certain point, the jet's internal pressure falls to match the external pressure and then dips below it. The external medium then squeezes the jet, forcing it to reconfine back to a narrower width. This sudden pinching creates a standing shock wave that wraps around the jet like a ring. As the jet continues its flow, it may go through cycles of expansion and reconfinement, creating a series of these standing shock rings, which we see as a chain of regularly spaced knots. In this model, the spacing isn't set by the timing of eruptions at the black hole, but by the physical properties of the jet and its environment, its speed, density, and the pressure of the surrounding gas. This elegantly explains why the spacing can be so uniform, but it also introduces a new set of variables, making it difficult to use the knots to directly probe the black hole's heartbeat. The ultimate challenge is that these different mechanisms, central engine pulsations, internal resonant cavities, and external reconfinement, can produce remarkably similar visual patterns from our distant vantage point. A chain of knots could be the signature of a black hole that feeds in a rhythmic, hiccuping fashion, or it could be the inevitable result of a steady jet interacting with a uniform external medium. To distinguish between them, we need to track the knots' motions and brightness changes with extreme precision over many years. We look to see if new knots are born at the jet's base with a regular clockwork timing, which would point strongly to a pulsating engine. Alternatively, if the knots appear to form further out and maintain their positions relative to each other, the reconfinement shock model becomes more likely. The reality is that both processes are probably at work in many jets, their effects intertwined, creating a complex, evolving pattern that no single theory can yet fully capture. These sound wave-like structures are therefore more than just beautiful cosmic decorations. They are a complex, encoded message about the stability of the engine and the nature of the space through which the jet travels, a message we are still learning how to read. Now, let's turn our attention from the brilliant light of the jets to something far more ghostly and elusive, a particle that barely interacts with the universe at all, the neutrino. For decades, these cosmic phantoms have streamed through the Earth by the trillions every second, passing through our planet and even our bodies as if they weren't even there, carrying secrets from the most violent corners of the cosmos. But catching one, and more importantly, tracing it back to its source, has been one of the greatest challenges in modern physics. This brings us to a landmark discovery that sent shockwaves through the astrophysics community, the first compelling evidence that directly linked a high-energy neutrino to a blazing jet from a supermassive black hole, opening an entirely new window onto these cosmic engines. The story begins in September 2017, when a single, exceptionally energetic neutrino struck the Ice Cube Neutrino Observatory, a colossal detector buried deep in the Antarctic ice. This wasn't just any neutrino, it was a cosmic messenger carrying an energy of nearly 300 tera-electron volts, making it one of the most powerful ever recorded. The key breakthrough was that, for the first time, Ice Cube's precision was sufficient to provide a rough but meaningful direction in the sky from which the particle had arrived. Almost simultaneously, telescopes across the globe and in space swiveled to look at that same patch of the cosmos. What they found was electrifying. A known blazar, a galaxy called TXS 0506+056, whose jet happens to be pointed directly at Earth, was in a state of extreme flaring, blazing with unusual ferocity in gamma rays. The coincidence in time and direction was too compelling to ignore. It strongly suggested that this single neutrino and the flaring jet were not just random neighbors, but were intimately connected. This connection is monumental because it provides a crucial, missing piece of the jet composition puzzle we discussed earlier. Remember the debate over whether jets are made of lightweight electrons or heavy protons. High-energy neutrinos like this one are the telltale signature of protons. They are created when these protons, accelerated to unbelievable energies within the jet, collide with other particles or with photons. These violent collisions produce a cascade of secondary particles, including short-lived particles called pions, which then decay to produce both gamma rays and neutrinos. So, the detection of a high-energy neutrino from a blazar is like finding a signed confession. It provides the first direct evidence that at least some jets are indeed filled with and accelerating protons, not just electrons. This confirms that these jets are not only brilliant light sources, but also powerful hadronic accelerators, capable of producing the building blocks of matter itself and flinging them across the universe. The implications of this single event ripple far beyond just one blazar, heralding a revolutionary new era of multi-messenger astronomy. For centuries, we have studied the universe almost exclusively through light photons of all energies, from radio waves to gamma rays. But light can be absorbed, scattered, or distorted on its long journey. Neutrinos, along with gravitational waves, offer a fundamentally different way to see the cosmos. They are messengers that travel virtually unimpeded, giving us a direct, uncontaminated view right into the heart of the most obscured and violent environments. When we can combine the information from a neutrino, a gamma-ray flare, and other forms of light all from the same object, it's like having multiple independent witnesses to a cosmic crime, each one providing a piece of the story that the others cannot. This multi-messenger approach allows us to finally move from speculation to confirmation, to truly prove what is happening in the heart of these jets. Yet, for all the excitement, a single event does not constitute a definitive proof, and the hunt is now on to solidify this connection. The core of the challenge lies in the neutrino's ghostly nature. While the pointing from IceCube was good, it was not pinpoint accurate. The error box for the neutrino's origin still covered a small but significant area of the sky, leaving a slight but real possibility that the flaring blazar was merely a fortunate bystander. Since that first detection, there have been a few other tantalizing correlations, but nothing with the same dramatic clarity. To move from a thrilling hint to a settled scientific fact, we need statistics. We need to see a pattern, a cluster of high-energy neutrinos that consistently arrive from the same direction on the sky, and better yet, that arrive at the same time as gamma-ray flares from a known jet. This requires patience and ever more sensitive detectors. The next generation of neutrino observatories, like the planned IceCube Gen 2 and the KM3 NET detector in the Mediterranean Sea, aim to catch far more of these elusive particles with even better directional accuracy, potentially providing the flood of data needed to make an undeniable case. There is also a fascinating theoretical debate swirling around this discovery. If jets like this one are indeed prolific neutrino factories, it places incredibly tight constraints on the conditions within them. The region where the proton collisions occur must be incredibly dense with target photons or other protons for these interactions to happen frequently enough to produce the flux of neutrinos we suspect. Some models suggest that the neutrinos are produced in the very innermost, most intense region of the jet, near the black hole, where the light from the accretion disk provides a thick fog of target photons. Others propose that the collisions happen further out, in standing shock waves or in the jet's interaction with clouds of interstellar material. Each scenario makes different predictions about how the neutrino emission should correlate with flaring in different parts of the electromagnetic spectrum. A bright X-ray flare might point to one origin, while a simultaneous optical and gamma-ray flare might point to another. By meticulously monitoring these blazars across every wavelength and waiting for the next neutrino to strike, we are essentially conducting a remote forensic analysis of the jet's internal structure, using these ghostly particles to probe realms that are utterly invisible to our telescopes. The connection to neutrino production, therefore, transforms the jet from a distant spectacle into a cosmic particle physics laboratory, offering us a unique opportunity to study fundamental processes of acceleration and interaction under conditions that we could never hope to recreate on Earth. But what happens when these cosmic beacons go dark? We've been talking about brilliant, high-energy jets lighting up the universe, but there's a compelling possibility that for much of their lives, these outflows might be operating in a kind of stealth mode. This brings us to our 20th unexplained feature, the enigma of dark jets in quiescent states. Imagine a supermassive black hole that has finished a large feast. Its accretion disk has been mostly consumed, and the rate of infalling matter has dropped to a mere trickle. The brilliant radio-loud quasar it once powered has faded into a quiet, unassuming galactic nucleus. According to our conventional understanding, the jet should have shut down entirely. Yet, there is growing suspicion that the engine might still be running, silently idling and producing a jet that is virtually invisible to our radio telescopes. This isn't a jet that has turned off, it's a jet that has learned to whisper. The key to this stealthy behavior lies in a concept we touched on earlier: radiatively inefficient accretion flows. When the accretion rate drops very low, the infalling gas becomes so hot and diffuse that it cannot cool efficiently. It forms a puffy, tenuous torus rather than a bright, thin disk. In this state, the energy released by friction and gravitational infall isn't radiated away as brilliant light. Instead, it is simply carried inward with the gas, a process called advection. This has a direct and crucial impact on the jet. If the jet is still being launched, perhaps by the black hole's spin tapping into its rotational energy via the Blandford-Zeenagic process, the plasma it contains will also be exceptionally hot and diffused. It will lack the dense population of ultra-relativistic electrons that produce the copious synchrotron radiation we normally see in radio waves. The jet is still there, carrying kinetic energy and momentum, but it's not lighting up its own path. It has become a dark or radiatively inefficient jet, a ghostly stream of power flowing out into the darkness. So if we can't see it in the radio, how could we possibly know it's there? This is where astronomers have to become cosmic detectives, looking for indirect clues and subtle footprints. One of the most promising methods is to look for the jet's impact on its surroundings. Even a dark jet carries immense kinetic energy. If this unseen beam plows into clouds of interstellar gas within its host galaxy, it will shock and heat that material, causing it to glow in specific wavelengths, particularly in the infrared or in optical emission lines like hydrogen alpha. We might see strange, elongated bubbles of warmed gas extending from the galactic center, with no obvious radio source to explain their existence. It would be like seeing the wake of an invisible ship moving through a cosmic sea. Another telltale sign could be the detection of X-rays. As the dark jet interacts with the intergalactic medium, it could create shock fronts that heat the surrounding gas to millions of degrees, causing it to emit faint X-rays that our space-based telescopes might just be able to pick up. Perhaps the most dramatic evidence for these dark outflows comes from our very own cosmic backyard, the center of the Milky Way. Our galaxy hosts a supermassive black hole, Sagittarius A, which is famously quiet and radio faint. For years, it was assumed to be jetless. However, observations from NASA Chandra X-ray Observatory have revealed a pair of colossal, bipolar bubbles of hot gas extending for thousands of light years above and below the galactic plane. Furthermore, the Fermi Gamma Ray Space Telescope has detected even larger enigmatic structures known as the Fermi bubbles, glowing in high-energy gamma rays. These gigantic features are difficult to explain without the past action of a powerful jet or wind from Sagittarius A. The leading theory is that our black hole experienced a period of activity in the relatively recent past, perhaps a few million years ago, and during that time it launched a jet. But the nature of that jet is hotly debated. Was it a brief, radio-loud outburst, or could it have been a longer-lasting, dark, radiatively inefficient outflow that efficiently channeled energy outwards without producing much radio glare? The existence of these vast structures suggests that even in its quiescent state or during periods of very low-level activity, a black hole can release a tremendous amount of energy in a form that is incredibly difficult to detect directly. This forces us to reconsider the true duty cycle of jet production. The brilliant, radio-bright jets we love to study may just be the loud, attention-grabbing phases. For most of a black hole's life, its primary output of energy might be through these dark, stealthy outflows, quietly shaping their galaxies from the shadows. The journey of a black hole jet does not end when it leaves its host galaxy, or even when it carves out its immense radio lobes. Its influence extends into the most vast and empty realms of the cosmos, the intergalactic medium itself. This is the thin, superheated gas that fills the space between galaxies, a relic from the dawn of time that forms the very backdrop of the universe. For eons, it was thought this medium was a relatively passive component, a quiet sea in which galaxies floated. But we now understand that jets are constantly stirring this cosmic ocean, pumping tremendous energy into it and, in the process, becoming architects of the universe's largest-scale structures. They act as colossal underwater geysers, heating the entire environment and preventing it from collapsing under its own gravity to form new galaxies, thereby regulating the growth of the cosmic web itself. The most direct and stunning evidence for this immense energy transfer comes from the giant cavities and ripples we observe in galaxy clusters. Using powerful X-ray telescopes like Chandra, astronomers have looked at the hearts of massive clusters and seen something astonishing: enormous dark bubbles seemingly carved out of the brilliant X-ray emitting hot gas that pervades the cluster. These are not holes in the traditional sense, but rather volumes of space that have been evacuated and filled with the magnetized plasma from the jet's radio lobes. The jet has literally pushed the intergalactic gas aside, creating a cosmic void. Surrounding these cavities, we often see delicate, shell-like structures, ripples of compressed gas, like sound waves frozen in the plasma. These are the direct echoes of the jet's fury, shock waves that have traveled outwards from the central black hole and deposited their energy into the surrounding medium, heating it further. Calculating the total energy involved in this process is a monumental task that reveals just how powerful these systems are. To create one of these cavities, the jet must do work against the pressure of the surrounding gas. By measuring the volume of the cavity and the local pressure, we can estimate this cavity power. The numbers that emerge are staggering. A single jet can inject the energy equivalent of billions of supernova explosions into the intergalactic medium over its lifetime. This energy doesn't just vanish, it thermalizes, meaning it is converted into heat, raising the temperature of the gas across the entire galaxy cluster by millions of degrees. This sustained heating is crucial. Without it, the dense central regions of the gas in galaxy clusters would cool rapidly, falling inward in a torrential, cooling flow that would fuel rampant star formation and feed the central black hole to unimaginable sizes. The jets provide a feedback mechanism that prevents this, maintaining a precarious thermal balance that keeps the cluster atmosphere hot and diffuse, effectively setting a thermostat for an entire metropolis of galaxies. However, measuring this energy input with precision is fraught with challenges that underscore the complexity of these systems. The first major hurdle is that the energy is not deposited in a single, neat package. It is delivered episodically in bursts that can be separated by millions of years. A black hole might be active for 10 million years, inflate a pair of cavities, and then fall quiet. By the time it reawakens, the previous cavities may have risen buoyantly away from the center, like giant hot air balloons, and begun to dissipate. We are often seeing a layered history of outbursts, making it difficult to sum up the total energy budget over the cluster's lifetime. Furthermore, the jet's energy isn't only in the form of the mechanical work needed to inflate the cavity. a significant but poorly measured fraction is carried away as sound waves and turbulence, which can travel vast distances and dissipate their energy in regions far from the cavity itself. This invisible energy is incredibly difficult to quantify, meaning our current estimates of the jet's total power are almost certainly lower limits. The long-term consequences of this continuous cosmic stirring are profound, shaping the destiny of matter on the very largest scales. This process, known as AGN feedback, is now a cornerstone of our modern understanding of cosmology. By preventing the excessive cooling of gas in the most massive halos, jets effectively put a brake on the growth of the most enormous galaxies. They explain why we don't see galaxies 100 times more massive than the ones we observe. The black hole at the center simply gets too powerful and shuts down its own fuel supply, along with that of the entire galaxy. This feedback also enriches the intergalactic medium, as the jets and the buoyant cavities they create can transport heavy elements forged in stellar furnaces out of their host galaxies and into the void, seeding the cosmic web with the raw materials for future generations of stars and planets. Ultimately, the impact of jets on the intergalactic medium transforms our view of black holes from isolated monsters to integrated components of the cosmic ecosystem. They are not just consuming matter, they are regulating the climate of the entire universe, influencing where and when new galaxies can form and grow. The vast, hot atmosphere of a galaxy cluster, once thought to be a serene and placid environment, is in reality a dynamic battlefield, shaped and heated by the intermittent roars from the supermassive black holes at its heart. This grand-scale feedback loop, connecting the smallest scales of space-time around a black hole to the largest structures in the cosmos, remains one of the most compelling and active areas of research, as we strive to understand how these dark engines write their signature across the fabric of the universe itself. Figuring out what fuels these breathtaking cosmic spectacles brings us face to face with a more fundamental question: where is the actual particle accelerator? We know the jet is packed with electrons and protons moving at a hair's breadth from the speed of light, but the jet itself is a structure that can stretch for millions of light years. So, where along that immense highway does the crucial act of acceleration happen? Is it a single, powerful engine at the very start, or are there multiple boost stations along the way? Astronomers are locked in a spirited debate over 3 primary locations, and each candidate site paints a dramatically different picture of how the jet manages its incredible energy output. The first and most intuitive candidate is the base of the jet, in the chaotic space just outside the black hole's event horizon. This region is a maelstrom of twisted magnetic fields and ferocious gravitational forces, a place where the raw power of the black hole's spin is directly channeled into the plasma. Here, the acceleration process could be almost instantaneous. Picture immense electric fields generated by the violently spinning magnetic fields that act like colossal particle cannons, flinging charges to relativistic speeds in a single, tremendous burst. The appeal of this central engine model is its sheer power and efficiency. It would mean the particles are born with most of their energy streaming away from the black hole already at near light speed, which would explain the high energies we observe right from the jet's launch point. However, this model faces a significant hurdle: the dense soup of radiation and matter near the black hole. In such a crowded environment, a newly accelerated particle would have a high probability of immediately colliding with a photon or another particle, losing its hard-won energy almost as quickly as it gained it. It's like trying to accelerate a car to top speed in the middle of a dense, gridlocked traffic jam. The potential is there, but the environment works against you. This leads us to the second major candidate: internal shocks and turbulent regions within the jet itself. Think of the jet not as a smooth, laminar flow, but as a cosmic highway with erratic traffic. Sometimes the central engine surges, sending a faster-moving parcel of plasma down the channel. This faster blob eventually catches up to a slower-moving parcel that was ejected earlier, When they collide, they don't just merge gently, they create a violent internal shock wave. This shock front acts as a natural and highly efficient particle accelerator. Charged particles can bounce back and forth across this magnetic barrier, trapped by the turbulence, gaining a little more energy with each crossing in a process known as diffusive shock acceleration. It's like a ping-pong ball being volleyed faster and faster between two approaching paddles. This model elegantly explains the bright knots and flares we often see within jets. Each one could be a site of ongoing internal collisions, providing a series of booster rockets that keep the particles energized along their long journey. This scenario also avoids the dense, hostile environment of the base, allowing acceleration to occur in a more spacious and forgiving part of the flow. The third potential site is all the way at the end of the line, the terminal shock, where the jet rams into the intergalactic medium and forms its giant radio lobes. This is arguably the most powerful accelerator of all. The jet, after traveling millions of light years, slams into a virtual wall of tenuous gas, coming to an abrupt and violent halt. The resulting shock wave is a cataclysm on an epic scale, a cosmic collision that converts the jet's entire bulk kinetic energy into heat, light, and most importantly, particle acceleration. The terminal shock provides a vast and turbulent region where particles can be trapped for long periods, cycling back and forth and gaining enormous energies. This could be the primary factory for the very highest energy cosmic rays, as the sheer scale of the shock front provides a runway long enough to push particles to their ultimate limits. The lobes that glow so brightly in radio waves are a testament to the incredible numbers of ultra-energetic electrons being accelerated and re-accelerated in this final, chaotic destination. The core of the mystery is that all three of these sites likely contribute to some degree, but determining which one is the dominant source for the particles we ultimately observe is a monumental challenge. The light that reaches our telescopes is a blended signal from every part of the jet, making it incredibly difficult to isolate the emission from one specific region. The particles themselves don't carry a label stating where they were born. To make progress, astronomers have to be clever, looking for specific clues in the light's properties. For instance, if we see a flare in high-energy gamma rays that is followed moments later by a flare in lower-energy radio waves from further down the jet, it suggests a shock wave is propagating outward, accelerating particles as it goes. This would strongly point to internal shocks as the key player. Alternatively, if we find that the highest energy photons and particles seem to be correlated with the giant lobes at the jet's end, it would bolster the case for the terminal shock. The debate is far from settled, and it's entirely possible that the balance of power shifts from one jet to another, or even within the same jet during different phases of its activity. Pinpointing the primary acceleration zone is not just an academic exercise, it is essential for understanding the jet's true energy budget, its stability, and its ultimate impact on the surrounding cosmos. Until we can trace a particle's journey from its birth to its final glow, a fundamental part of the jet's mysterious engine will remain hidden in plain sight. To truly understand the nature of a black hole jet, you can't just look at it through a single lens, focusing only on its radio glow or its X-ray flare. You have to step back and see the whole picture across the entire electromagnetic spectrum, from the long, rolling waves of radio to the razor-sharp spikes of gamma rays. This complete portrait of a jet's brightness at every possible energy is what scientists call its spectral energy distribution, or SED. Think of it as the jet's unique cosmic fingerprint, a detailed chemical signature written in light that holds the secrets to the particles, magnetic fields, and physical processes operating within it. Each jet, from the quiet ones in nearby galaxies to the blazing blazars pointed right at us, paints its own distinct SED on the sky, and learning to read these intricate patterns is one of the most powerful and challenging tasks in modern astrophysics. A typical SED for a powerful jet is a story told in two dramatic acts, often appearing as a distinct double-humped curve when plotted on a graph. The first hump, usually peaking in the infrared, optical, or ultraviolet part of the spectrum, comes from a process we've discussed before: synchrotron radiation. This is the light emitted by electrons and sometimes positrons as they spiral at near light speed around the jet's magnetic field lines. The location and height of this synchrotron hump tell us directly about the energy of these electrons. A peak at higher frequencies means the electrons are more energetic, whipping around in a more violent dance. The second hump, which can rise to even greater heights in the gamma-ray region, is where the story gets even more interesting. This is widely believed to be produced by inverse Compton scattering, the powerful process where those same high-speed electrons slam into lower-energy photons, boosting them to tremendous energies. The photons being targeted could be the synchrotron photons from the first hump itself, or they could be external photons like those from the hot accretion disk, the bright gas clouds of the broadline region, or even the cosmic microwave background. The precise shape of this second hump is a sensitive probe of the density and type of these target photons, offering a window into the jet's environment. The monumental challenge, the core of the modeling mystery, is that no single, simple population of electrons can satisfactorily explain the entire SD for many jets. If you try to use one group of electrons with a single, smooth distribution of energies to produce both the low-energy synchrotron hump and the high-energy Compton hump, the model almost always breaks down. It might get the general shape right, but it fails spectacularly to match the precise details, particularly the extreme ends of the spectrum like the very high-energy gamma rays or the low-frequency radio waves. To make the models fit the exquisite data we now collect from telescopes like the Hubble, Chandra, and Fermi, astrophysicists are forced to invoke multiple, distinct particle populations coexisting within the same jet. It's as if you were analyzing the exhaust of a car and found you needed to account for two completely different types of fuel burning in separate, hidden engines to explain the entire chemical signature. So, what might these separate populations look like? One compelling idea is a stratified jet, a structure with a fast, narrow spine surrounded by a slower, denser sheath. The spine racing along at a different velocity and immersed in its own magnetic environment could be filled with one class of ultra-energetic electrons responsible for the highest energy gamma rays. Meanwhile, the sheath, plowing through more material and subject to different shocks, could contain a separate, cooler population of electrons that dominate the emission in the ultraviolet and X-ray parts of the spectrum. Another possibility is that these populations are separated in time and space rather than in structure. A recent, powerful shock wave from a black hole eruption could have injected a fresh batch of extremely energetic particles into the jet. These newcomers would produce their own distinct signature on the SD, superimposed on the more settled background emission from the older, more relaxed particles that have been traveling in the jet for much longer. We are essentially seeing the layered history of the jet's activity frozen in its light. This necessity for complex models reveals a far more intricate and messy reality than the simple, elegant jets we often imagine. The SED is a clear message that the interior of a jet is not a uniform soup, but a dynamically evolving and highly structured ecosystem. It forces us to ask difficult questions. How are these different particle populations accelerated and then kept separate? Do they originate in different parts of the central engine, or are they created at different shock fronts along the jet's path? How do they interact with each other, and why don't they simply mix together into a single, average population? The inability to find a one-size-fits-all model for every jet further deepens the mystery, suggesting that the recipe for a jet's internal makeup, the balance between its different particle groups, might be unique to each black hole system, dictated by its individual spin, accretion mode, and environmental factors. The spectral energy distribution, therefore, is more than just a fingerprint. It is a complex and unsolved equation, a cosmic cipher that we are only beginning to learn how to decode, revealing just how much we have yet to learn about the turbulent life within these magnificent beams of power. But what if we could find a way to see not just the direction of the jet's magnetic field, but also to measure its strength and sense its intricate, hidden twists along our entire line of sight? This brings us to a subtle yet incredibly powerful diagnostic tool known as Faraday rotation. The principle is beautifully elegant. As polarized radio waves travel through a magnetized plasma, like the hot gas surrounding a black hole jet, their polarization angle is gradually rotated. It's as if the magnetic field is acting like a cosmic crystal, subtly twisting the light that passes through it. The amount of this rotation is directly proportional to the strength of the magnetic field component along our line of sight and the density of free electrons in the plasma. By meticulously measuring this effect across different radio frequencies, astronomers can calculate a quantity called the Faraday rotation measure, effectively creating a three-dimensional probe that can sense the hidden magnetic environment shrouding the jet. For a long time, the simplest expectation was that the regions around powerful jets would exhibit a smooth, orderly gradient in their Faraday rotation. The idea was that a large-scale, coherent magnetic field, perhaps originating from the black hole's accretion disk, would envelop the system. In this clean picture, you would measure a rotation that changes gradually and predictably as you look through different parts of the halo around the jet, painting a portrait of a well-behaved and organized magnetic sheath. Such a finding would have been a triumphant confirmation of our more straightforward theoretical models, showing that the fields which launch and guide the jet also maintain their majestic order on vast scales. The reality, as revealed by our most sensitive radio telescope arrays, has been a spectacular and bewildering surprise. Instead of these smooth, gentle gradients, we see Faraday rotation measures that are incredibly complex and tangled. The data often looks like a chaotic patchwork quilt of positive and negative values, with sharp boundaries and sudden reversals existing right next to each other. This means that along a single line of sight, the radio waves are being twisted first in one direction and then in the opposite direction by different layers of magnetized plasma. The clear implication is that the magnetic environment around these jets is not a simple, ordered structure. It is a turbulent, mixed-up mess of fields pointing in all directions, a frothing sea of magnetic chaos that defies any easy description. This tangled picture forces a dramatic rethinking of the jet's relationship with its surroundings. One compelling explanation for this chaos is that the jet itself is actively stirring the pot. As the powerful beam plows through the halo of hot gas surrounding its host galaxy, it doesn't just push it aside neatly. It drives powerful turbulence, creating whirlpools and eddies in the plasma that stretch, twist, and tangle the magnetic fields frozen within it. Imagine dragging a giant spoon through a cup of coffee with milk. You don't create orderly layers, you create a swirling, intermixed mess. The jet is that spoon on a galactic scale, and the Faraday rotation is showing us the resulting magnetic froth. In this scenario, the observed patchwork is a direct map of this ongoing turbulence, a snapshot of the violent interaction between the jet and the galactic atmosphere it is trying to escape. Another fascinating possibility is that we are witnessing the imprint of many past outbursts from the black hole. A supermassive black hole isn't always active. It has periods of feeding and fasting. Each time it turns on, it can launch a new jet, possibly in a slightly different direction if the accretion disk has been perturbed. These multiple episodes of activity would inflate different bubbles of magnetized plasma into the surrounding space, each with its own distinct magnetic field orientation. Over millions of years, these bubbles would overlap and intermingle, creating a layered and complex fossil record of the black hole's violent history. The chaotic Faraday rotation we measure today could be the superimposed signature of all these past eruptions, a palimpsest of magnetic fields written over each other, making it nearly impossible to disentangle the story of any single event. The presence of such a disorganized magnetic environment has profound consequences for the jet itself. A turbulent, mixed-up external field can act as a source of friction and instability for the jet, potentially causing it to wobble, bend, or even dissipate its energy more quickly. This might explain why some jets appear knotted and disrupted, while others remain remarkably straight. It also complicates the picture of how the jet remains collimated. If the confining pressure from the external medium is accompanied by such a chaotic magnetic field, the simple models of magnetic pinching become vastly more difficult to calculate. The Faraday rotation mystery, therefore, does more than just reveal a messy magnetic field. It challenges our understanding of the jet's stability and longevity, suggesting that its journey through intergalactic space is a constant battle against a turbulent and magnetically complex medium that is anything but placid and orderly. Pondering the lifespan of a black hole jet forces us to confront a timescale that is almost alien to human experience. We are not talking about something that lasts for a human lifetime or even for the entire history of our civilization. We are grappling with an engine that can be active for millions of years, fall silent for tens of millions more, and then roar back to life in a cycle that may repeat over the entire multi-billion-year life of a galaxy. This rhythm of activity, known as the jet's duty cycle, is a fundamental property that dictates its total impact on the cosmos. Is a jet a brief, brilliant flash like a cosmic firework, or is it a near-permanent feature, a steady blowtorch that rarely, if ever, shuts off? The answer holds the key to calculating the true, integrated energy a single black hole can inject into the universe, transforming it from a spectacular event into a dominant force in galactic evolution. The evidence for this episodic behavior is written across the sky in the vast, often complex structures of radio lobes. In many giant elliptical galaxies, we don't see just one simple pair of lobes, we see nested, ghostly structures. A young, bright, and powerful set of lobes might be visible close to the galaxy, energized by a jet that is currently active. But further out, we can often detect much larger, fainter, and more diffuse radio emissions, the fading remnants of a jet that was active hundreds of millions of years ago. These are fossil jets, the celestial ghosts of past eruptions. Their very existence is a clear declaration that the central engine has an on-off switch. The black hole feasted, launched a jet that inflated a massive bubble of radio-emitting plasma, and then its food supply was cut off or it entered a quiescent state. The jet turned off and the lobe began to fade as its most energetic electrons slowly lost their energy and stopped producing strong synchrotron radiation. The fact that we can still detect these ancient fossils tells us that the magnetic fields and lower energy particles can persist for astonishingly long times, providing a tangible record of the black hole's violent past. Determining the precise active lifetime of any single jet, however, is a challenge of immense proportions. We are, in essence, trying to measure the duration of a single heartbeat by looking at a creature that lives for 1,000 years, and we only get to observe it for a single second. Our direct observations of jet activity span mere decades, a blink of an eye on the cosmic clock. To estimate a jet's lifetime, we must become cosmic archaeologists, piecing together the story from indirect clues. One primary method involves measuring the total size of the radio lobes and dividing by the estimated speed of the jet's advancing head. If a lobe is 300,000 light-years across and the jet is plowing through the intergalactic medium at 1/10 the speed of light, the simple calculation suggests the jet has been actively inflating that lobe for about 3 million years. But this is a crude estimate fraught with uncertainty. The jet speed may not have been constant. It could have started slowly, accelerated, or been stalled by dense clouds of gas. The external pressure of the surrounding medium can also vary dramatically, affecting the expansion rate. Furthermore, the concept of a single, continuous lifetime might be a dramatic oversimplification. A jet may not have one long, stable life, but rather a stuttering existence of many short, violent bursts. Imagine a black hole that experiences a minor instability in its accretion disk every 50,000 years, sending a fresh surge of power down the jet for a brief period of 10,000 years. Over the course of 100 million years, this would create 2,000 separate episodes of activity. From our distant viewpoint, the jet might appear to be permanently on, when in reality it is flickering on and off like a faulty neon sign. The complex, filamentary, and knotted structures we see within many jets and lobes strongly support this idea of a chaotic, bursty duty cycle. Each knot could be the relic of a distinct outburst, a separate injection of energy from the central engine. This makes the calculation of a total active lifetime even more difficult, as we are trying to sum up the duration of countless individual pulses that we can no longer resolve in time. The implications of the duty cycle for the jet's total energy output cannot be overstated. Consider the difference between a light bulb left on for a century and a strobe light that flashes for 1 second every hour. The total energy consumed is vastly different. For a black hole jet, this integrated energy is what truly shapes its host galaxy and the surrounding intergalactic medium. A jet with a high duty cycle, one that is active for, say, 50% of its existence, is a relentless, persistent heating source. It can maintain a constant high pressure in the galactic halo, effectively preventing any gas from cooling and falling in to form new stars, permanently enforcing a red and dead state on the galaxy. In contrast, a jet with a very low duty cycle, one that only erupts for 1% of the time, is a cosmic cataclysm. Its eruptions are like occasional, violent earthquakes. Each outburst can be incredibly powerful, blowing vast cavities in the galactic gas and driving massive shock waves, but the system has long periods of quiet in between where the gas can slowly cool and attempt to recover. This stop-start pattern might actually lead to episodic bursts of star formation, a punctuated equilibrium in the life of a galaxy dictated by the irregular feeding habits of its central black hole. The ultimate mystery, then, is what governs this fundamental rhythm. What determines the timing of the black hole's feast and famine? The answer likely lies in a complex feedback loop between the jet and its fuel source. A powerful jet can heat and disperse the very gas reservoir that feeds the accretion disk, effectively starving the black hole and forcing the jet to shut down. Once the jet is off, the hot gas can slowly cool and fall back toward the center over tens of millions of years, eventually reaching a critical density that triggers a new round of intense accretion and jet activity. The duty cycle is therefore a self-regulating property of the system, a natural oscillation between outburst and quiescence. The frequency and duration of these cycles depend on delicate balances, the total mass of the gas halo, the efficiency of the jet at heating it, and the rate at which the gas can cool. This transforms our view of the supermassive black hole from a simple monster into the beating heart of the galaxy, whose rhythm of activity, its lifetime and duty cycle, orchestrates the long-term fate of the billions of stars that swirl around it. Now, let's complicate this picture even further by introducing a second monster into the lair. Imagine not one, but two supermassive black holes locked in a gravitational dance at the center of a galaxy, the final product of a cosmic merger between two once separate star systems. This binary black hole scenario transforms the relatively stable engine room into a chaotic, whirling carnival ride, with profound and often bizarre consequences for any jet trying to form. The presence of a second gravitational giant doesn't just add power, it introduces a wild, unpredictable variable that can twist, interrupt, or even supercharge the jet in ways a single black hole never could. The most dramatic effect of this binary dance is likely on the jet's direction. If a jet is launched from one of the black holes, the orbital motion of the binary system can cause the entire jet to precess or wobble in a complex and evolving pattern. Unlike the smooth precession from a single spinning black hole, the wobble induced by a binary companion is far more extreme. Picture a spinning top that isn't just wobbling on its own axis, but is also being swung around in a wide circle by a child. The resulting motion is a complex superposition of both rotations. For a jet, this means its beam could trace out a wild, spiraling path through intergalactic space, like a celestial garden sprinkler on a wobbly mount. In some cases, this precession could be so severe that the jet periodically points directly at its own accretion disk or the companion black hole's disk, leading to violent interactions that disrupt the flow and cause massive outbursts of energy. We might even see jets that appear to be bent or helical on truly colossal scales, a fossilized record of this ancient orbital dance. But what if the binary's influence is even more disruptive? The gravitational tug of war between two supermassive black holes can wreak havoc on the very fuel supply needed to power the jets. The accretion disks around each black hole can be periodically torn apart, their gas stripped away or funneled into chaotic, unpredictable streams. This could lead to a jet that is intrinsically intermittent, turning on and off not because of internal disk instabilities, but because the external gravitational environment is constantly changing. One black hole might be actively feeding and producing a brilliant jet, only for its companion to swing by on its orbit and gravitationally steal away its fuel source, causing the jet to sputter and die. The system could then flip, with the second black hole briefly activating its own jet before the cycle repeats. The result would be a cosmic seesaw of jet activity, a periodic launching and quenching tied directly to the orbital period of the binary, which could range from years to centuries. The hunt for observational evidence of these chaotic binary systems is one of the most exciting treasure hunts in modern astrophysics. Astronomers are actively searching for specific telltale signatures. One of the most sought after is a sinusoidal or sine wave pattern in the jet's apparent position on the sky. If we could track a bright knot in a jet over many years and see its path deviate in a smooth, repeating wave, it would be a powerful indicator of orbital-induced precession. Another promising signature is periodic variability in the jet's brightness. If the jet's power is being modulated by the binary's orbit, for instance, if it brightens every time the black holes are at their closest approach and fuel is most violently funneled inward, we would see a regular heartbeat in the light curve, a clockwork flicker spanning decades. There are even more exotic possibilities, like the detection of two separate, misaligned jets emanating from the same galactic center, a clear sign of two independent engines at work. Or we might see a single jet that appears to be suddenly and sharply deflected, as if it has slammed into the accretion disk or the powerful wind of its unseen companion. While a handful of compelling candidates for supermassive black hole binaries exist, conclusive proof remains elusive. The timescales involved are often longer than a human lifetime, and the spatial scales are so small that resolving two distinct black holes is at the very limit of our current telescopic power. However, the upcoming Laser Interferometer Space Antenna, or LISA, a future gravitational wave observatory, is designed to directly detect the ripples in space-time from these colossal mergers. LISA will hear the final inspiral of supermassive binary black holes, providing a census of these systems and confirming their existence. Until then, the influence of binary black holes on jet production remains a captivating theoretical playground, a demonstration of how the simple, elegant physics of a single engine can be transformed into a spectacularly complex and unpredictable spectacle when the universe decides to double down on its darkness. Now we arrive at a feature that pushes our understanding of reality to its absolute limit, venturing from the cosmic scale down to the very fabric of space and time itself. This is the realm of quantum gravity speculation, where the immense energies and vast distances of black hole jets might provide our first ever glimpse into a theory that has eluded physicists for a century. The quest is to unite Einstein's theory of general relativity, which governs the gravity of planets, stars, and black holes, with quantum mechanics, the rulebook for the atomic and subatomic world. These two pillars of modern physics are fundamentally incompatible, and finding a way to marry them into a single theory of quantum gravity is arguably the greatest unsolved problem in fundamental physics. The stunning proposal is that the violent, fluctuating light from these jets could carry subtle fingerprints of this unified theory, making them nature's own particle accelerators for probing the deepest laws of the cosmos. The core of this tantalizing idea rests on a concept known as Lorentz invariance violation. In our everyday world and in all of Einstein's relativity, the speed of light in a vacuum is a constant, an unwavering universal speed limit that is the same for all observers and for all colors of light. This principle is a cornerstone of modern physics. However, many theories of quantum gravity suggest that at an unimaginably tiny scale, the Planck scale, which is 1 billion times smaller than a proton, the smooth, continuous nature of space-time might break down. Instead, space-time might have a granular, foamy structure, often called quantum foam. The hypothesis is that as photons travel across billions of light-years through this foamy texture, the highest energy photons, with their incredibly small wavelengths, might interact with this granularity slightly differently than lower energy photons. They wouldn't travel on a perfectly smooth road, but on one with minuscule bumps. This could cause a tiny cumulative delay, a spectral lag, where the highest energy gamma-ray photons arrive at our telescopes a fraction of a second after their lower energy counterparts, even though they were emitted at the exact same instant from the same cataclysmic event in the jet. This is where the phenomenal properties of black hole jets become essential. To have any hope of detecting such a minuscule effect, you need an ideal laboratory. The laboratory must produce extremely high-energy photons. It must be located at a colossal distance to allow the effect to accumulate over billions of light-years of travel. And it must produce sharp, unpredictable flares so we have a clean, timable signal. Blazars, those active galaxies with jets pointed directly at us, fit this description perfectly. They produce flares of light across the entire electromagnetic spectrum, from radio waves to tera-electron-volt gamma rays, and they can do so from the far reaches of the observable universe. When a blazar flares, it creates a brief, well-defined starting pistol shot. By meticulously comparing the arrival times of gamma rays of different energies from that single flare, astronomers can hunt for this telltale signature of quantum foam. It's an experiment of breathtaking precision, trying to measure a delay that might be a mere millisecond over a journey of 10 billion years. The challenge, however, is that the universe is filled with more mundane explanations that can mimic this quantum gravity signal. The jet's own internal physics is incredibly complex. The light we see is not created in a single point-like region. The highest energy gamma rays might be produced in a different part of the jet than the lower energy gamma rays, or they might be created through a slightly different physical process that has its own intrinsic time delay. A shock wave propagating through the jet will accelerate particles gradually, with higher energy particles taking a fraction longer to reach their peak energy. This would naturally cause the highest energy emission to peak slightly later in time, creating a delay that has absolutely nothing to do with quantum gravity, but everything to do with the astrophysics of the jet itself. Disentangling this astrophysical background from a potential fundamental physics signal is the central obstacle in this entire field of research. It requires building incredibly detailed models of jet emission to predict the intrinsic time lags, so we can then look for any additional delay that might be the true signature of quantum spacetime. Despite these immense hurdles, a few tantalizing and highly controversial reports have emerged over the years. Some analyses of gamma-ray flares from distant blazars have claimed to detect delays consistent with certain models of quantum gravity. These findings send ripples of excitement through the theoretical physics community, as they suggest we might finally be peering into a realm beyond Einstein. However, these claims are met with intense and appropriate skepticism. The sample sizes are small, the statistical significance is often marginal, and other research teams analyzing the same data frequently find that the delays can be explained by standard astrophysical processes within the jets. The true significance of any single measurement is difficult to assess, and what one group might hail as a revolution, another dismisses as noise or modeling error. This healthy, vigorous debate is the hallmark of a science operating at its very frontier. Ultimately, the search for quantum gravity signals in blazar light represents a beautiful synergy between the largest and smallest scales in the universe. It transforms cataclysmic events around supermassive black holes into precision instruments for fundamental physics. Even the repeated failure to find a definitive signal is profoundly informative, as it places ever more stringent limits on the possible theories of quantum gravity, ruling out entire classes of models that predicted effects that are too large. Each new gamma-ray flare from a distant blazar is a new roll of the cosmic dice, offering another chance to catch nature in the act of revealing its deepest secrets. While a conclusive discovery remains elusive, the very possibility that we can use these cosmic beacons to test the fabric of space-time underscores their role not just as astronomical wonders, but as indispensable guides on our journey to a complete theory of the universe. This brings us to a fundamental accounting problem in cosmic energy, a discrepancy so stark it challenges our very understanding of how these engines operate. We call this the missing kinetic energy problem. It's a puzzle that arises when we try to balance the books on the jet's power output. On one side of the ledger, we can estimate the kinetic power of the jet, the raw, brute force it carries as it rams into the surrounding intergalactic gas and inflates those gigantic cavities and radio lobes. We calculate this by measuring the size of the cavities and the pressure of the external gas, then determining how much work the jet had to do to push that space open. The numbers we get are staggering, often requiring powers equivalent to the total energy output of billions of suns, sustained for millions of years. Now we turn to the other side of the ledger, the energy income. The primary source of fuel for the entire system is the gravitational energy released by matter spiraling inward through the accretion disk toward the black hole. There is a theoretical maximum to this process known as the Eddington limit, which represents a balance between the outward radiation pressure and the inward pull of gravity. But even for a powerfully feeding black hole, the energy available from accretion has a ceiling. And here lies the core of the mystery. In several well-studied systems, the calculated kinetic power of the jet seems to rival or even exceed the total radiant power available from the accretion process. It's as if a factory is producing more finished product than the total value of the raw materials we see being delivered to its loading dock. This forces a difficult question: where is all this extra kinetic energy coming from? The most compelling resolution to this paradox points directly to the black hole's spin as the hidden battery. This is where the elegant Blandford-Zeenagic process we discussed earlier becomes absolutely crucial. The energy from accretion is significant, but it's ultimately limited by the mass of the infalling material. The rotational energy of a spinning black hole, however, is a separate and vast reservoir of power. A maximally spinning black hole can store up to 29% of its rest mass energy as rotational energy, a truly colossal amount. The theory suggests that the jet launching mechanism can tap directly into this spin energy, using the black hole's twisted magnetic fields as a cosmic transmission belt. In this scenario, the accretion disk isn't the sole power source. It's more like a catalyst that helps build and sustain the magnetic structure that allows the black hole to unlock its own rotational inertia. The jet, therefore, is powered by a hybrid engine, part accretion energy, part black hole spin. This could easily explain how the kinetic power surpasses the pure accretion luminosity, because we're now drawing from two different bank accounts. The efficiency of this process can be mind-boggling, potentially exceeding 100% when compared to the accretion power alone, because it's converting the black hole's intrinsic rotation into outward thrust. However, this elegant solution immediately raises a new and thorny observational challenge. If the spin energy is the key to closing the energy budget, then the most powerful jets absolutely must be powered by black holes that are spinning at a tremendous rate. Yet, as we've explored, directly measuring a black hole's spin is one of the most difficult tasks in all of astrophysics. Our methods are indirect, relying on interpreting the X-ray light from the inner accretion disk, and they come with significant margins of error. For the specific systems where this kinetic energy problem is most acute, we often lack a precise, confirmed, and universally accepted measurement of the spin. We are in the frustrating position of having a beautiful theoretical solution that perfectly resolves the energy discrepancy, but we cannot yet independently verify its primary prediction across a large sample of jets. It's like knowing that a suspect has a motive that perfectly explains a crime, but we can't place them definitively at the scene. This pushes the development of better spin measurement techniques to the forefront of observational astronomy, as confirming the spin connection is the logical key to solving the missing energy mystery. Another fascinating layer to this puzzle involves the very way we measure the jet's kinetic power. Our primary method relies on the assumption that the work done to inflate the cavities in the hot gas is a direct and efficient representation of the jet's total power. But what if the system is even more efficient than we think? The calculations for cavity power are actually quite conservative. They often represent a lower limit. They account for the energy required to push the gas aside to create the cavity, plus the thermal energy now contained within the pressurized bubble. But they frequently do not account for other significant energy losses. For instance, a great deal of energy can be carried away as sound waves and turbulence in the surrounding gas, phenomena we can sometimes see as ripples in X-ray images but find difficult to quantify precisely. There's also the energy required to accelerate the cosmic rays that make the lobes glow in radio waves. If we could somehow add up all these other channels, the sound, the turbulence, the particle acceleration, the total power budget of the jet might be even higher than our current cavity estimates suggest. This would make the missing energy problem even more severe, intensifying the need for an ultra-efficient engine like a rapidly spinning black hole and pushing the limits of what we believe is physically possible. This leads to the provocative possibility that our understanding of the accretion process itself might be incomplete. Most of our estimates for the available accretion energy are based on the light we see, the luminosity. But what if a large fraction of the accretion energy is channeled directly into the jet in a form we cannot easily see? In the radiatively inefficient accretion flows associated with some of the most powerful jets, the energy released by gravitational infall isn't converted into light. It is advected, or carried inward with the gas, and could potentially be dumped directly into the jet launching mechanism at the event horizon. In this dark or kinetic mode of accretion, the system could be far more efficient at converting infalling mass into jet thrust than into visible light. The jet would appear overpowered compared to the galaxy's glow, not because it's breaking the laws of physics, but because the accretion process is fundamentally geared toward producing a powerful, low radiation outflow. The energy isn't missing, it was simply never converted into a form our optical and X-ray telescopes are designed to capture. We've been looking for the energy in the brilliant light of the feast, when in reality, the lion's share was being silently funneled into the jet's kinetic thrust all along. This reframing suggests that the true accounting of a black hole's energy output must look beyond its brightness and deeply consider the invisible but immensely powerful force of its wind. And now we venture into the very heart of what generates the dazzling light show of a black hole jet, a debate that splits the astrophysics community into two competing camps. This is the great hadronic versus leptonic debate, a fundamental disagreement over the identity of the primary particles responsible for the jet's most energetic radiation. On one side, the leptonic models argue that lightweight electrons and their antimatter partners positrons are the sole protagonists. On the other, hadronic models insist that heavy protons and atomic nuclei play the dominant role. While it might sound like an arcane technicality, the choice between these two scenarios forces us to confront wildly different realities about the jet's power, its composition, and its ultimate purpose in the cosmos. To understand the leptonic perspective, picture a jet filled with a vast sea of ultra-relativistic electrons. As these charged particles spiral along the jet's powerful magnetic field lines, they emit synchrotron radiation, which creates the jet's brilliant glow from radio waves up to X-rays. This is the first hump in the spectral energy distribution, but the story doesn't end there. These same high-speed electrons can then collide with the very synchrotron photons they just created. In a process we've discussed called inverse Compton scattering, the electrons transfer a massive amount of energy to these lower-energy photons, boosting them into the high-energy gamma-ray regime. This elegant two-step leptonic dance uses a single population of electrons to explain the jet's entire emission spectrum, from the lowest radio frequencies to the highest energy gamma rays. It's a beautifully parsimonious model, requiring only electrons and magnetic fields ingredients we know for certain are present. It suggests the jet is a lean, efficient machine, a focused beam of light particles and energy. Now consider the hadronic alternative. In this scenario, the jet is a far more substantial and powerful entity, loaded with heavy protons and ions. The synchrotron emission is still produced by a small population of electrons, but the real power behind the high-energy gamma rays comes from the protons. Imagine these protons being accelerated to unimaginable energies within the jet. When they collide with other particles or with lower energy photons, they produce a shower of secondary particles, including short-lived pions. These pions then decay, producing not only gamma rays but also neutrinos and more electrons and positrons. This proton-induced cascade is a much more complex and energetically expensive chain reaction. For a hadronic jet to produce the same brilliance in gamma rays as a leptonic one, it must contain a colossal amount of power locked away in these invisible protons. It transforms our view of the jet from a sleek beam of light into a dense, matter-laden cannonball, carrying enormous kinetic energy and raw mass across intergalactic space. The profound challenge, and the reason this debate remains so heated, is that from our distant vantage point, the light signatures produced by these two completely different physical processes can be virtually identical. A brilliant flare of gamma rays observed by the Fermi satellite could be perfectly explained by a leptonic model where electrons upscatter photons, or by a hadronic model where a beam of protons collides with a cloud of material. The final observational product, a spike of light at a specific energy, does not come with a label stating its origin. It's the ultimate cosmic disguise. We are like detectives trying to identify a suspect by only seeing their shadow on a wall. The outline is clear, but the true identity remains infuriatingly hidden. This ambiguity forces astronomers to become incredibly clever, searching for subtle, indirect clues that might betray the true culprit. One of the most critical pieces of evidence is the jet's timescale for variability. Leptonic processes involving nimble electrons can respond almost instantly to changes in the jet. An electron can be accelerated and radiate its energy away in a matter of seconds or minutes. Hadronic processes, by contrast, are generally slower. a heavy proton takes longer to accelerate to extreme energies, and the subsequent chain of pion production and decay introduces its own inherent time delays. Therefore, if we observe a jet that doubles its gamma-ray brightness in a matter of minutes, it strongly favors a leptonic origin, as it's difficult for a hadronic process to be that agile. However, this is not a perfect test, as under certain extreme conditions, hadronic models can also be tuned to produce rapid flares, blurring the lines once again. Another crucial clue lies in the connection to neutrinos. This is where the hadronic model has a potential smoking gun. Neutrinos are the ghostly byproducts of proton-proton and proton-photon collisions. If a jet flare is caused by a hadronic process, it should be accompanied by a flash of high-energy neutrinos. The leptonic process, in contrast, produces no neutrinos at all. The landmark detection of a high-energy neutrino from the Blazar TXS 0506+056 was therefore a monumental event, providing the first direct evidence that at least some jets are indeed capable of accelerating protons to immense energies. Yet, even this is not a total victory for the hadronic camp. The question remains, are protons the dominant source of the gamma rays, or are they merely a secondary player, with electrons still doing the bulk of the radiative work? A single neutrino confirms that protons are present and being accelerated, but it doesn't automatically prove they are responsible for the entire show. The implications of this debate ripple through every aspect of jet physics. If the leptonic view is correct, our estimates of the jet's total power are more moderate, as electrons are efficient radiators but don't carry much kinetic energy. The jet is a brilliant but relatively lightweight phenomenon. If the hadronic view prevails, the energy budget of the jet skyrockets. Accelerating and launching heavy protons requires orders of magnitude more power, suggesting the central black hole engine is far more efficient and potent than we ever imagined. A hadronic jet would also be a primary source for the ultra-high-energy cosmic rays that bombard our atmosphere, solving a century-old mystery in astrophysics. The composition of the jet, whether it is light or heavy, directly influences how it interacts with its environment, how much momentum it transfers to the intergalactic medium, and how effectively it can enact feedback on its host galaxy. The most likely resolution to this long-standing puzzle is that the universe refuses to be painted with a single brush. It is entirely probable that both processes are at work, with their relative importance shifting from one jet to another, or even within different regions of the same jet. A quasar in a dense galactic environment might favor hadronic processes as its jet rams into clouds of gas, while a blazar in a more pristine region might be predominantly leptonic. The jet's age, its power, and the diet of its black hole could all determine the dominant particle population. This ongoing scientific quest is far more than a theoretical exercise. It is a fundamental effort to weigh the contents of the most powerful beams in the universe, to understand whether they are ethereal whispers of light or substantial rivers of matter, and in doing so, to finally measure the true might of the darkness from which they erupt. From the colossal fury of quasars to the steady power of radio galaxies, we've assumed that a robust, well-fed accretion disk is the essential partner for launching a jet, providing both the fuel and the magnetic architecture needed to power up the beam. But the cosmos is a master of exceptions, and it presents us with a class of black holes that defy this very premise. These are the systems that appear to be almost starved of fuel, with accretion rates so pitifully low that they should be incapable of any significant activity. They are the so-called bald black holes, and their existence, quietly producing jets in near-starvation mode, forces us to question if we've been missing a fundamental piece of the jet launching puzzle all along. The standard model for jet formation paints a picture of a dynamic partnership. A substantial accretion disk provides the raw material, and as it churns, it acts as a powerful dynamo, generating and amplifying the magnetic fields that are crucial for the Blandford-Zeenagic process. The disk is the factory that builds the magnetic slingshot. When you see a brilliant, powerful jet, you naturally assume there is a vibrant, well-stocked disk fueling it. But a bald black hole turns this logic on its head. Its accretion flow is not a bright, thin disk, but a faint, puffy, and incredibly tenuous cloud of hot gas, a radiatively inefficient flow where so little matter is falling in that the system is effectively in a state of fasting. According to our textbooks, such a black hole should be dormant, its jet-launching machinery shut down due to a lack of magnetic fuel. The fact that we observe jets from these systems is like finding a car engine roaring to life with its fuel line disconnected. It suggests there is a way to power the jet that bypasses the traditional disk-based dynamo entirely. This startling observation immediately points the finger at the black hole's spin as the lone actor in this minimalist drama. If the accretion flow is too weak to generate strong magnetic fields on its own, then the only other source of immense power is the black hole's own stored rotational energy. The Blandford-Zeenagic process, in its purest form, posits that a spinning black hole can power a jet by twisting magnetic fields that are already present. The question for bald black holes is not how the disk generates new fields, but how sufficient magnetic flux is delivered and maintained near the event horizon in the first place, especially when the flow of incoming matter is just a trickle. One provocative solution is that these systems might exist in a kind of magnetic perfection from the very beginning. Perhaps the black hole formed with a strong, primordial magnetic field frozen into it from the collapse of its progenitor star, or maybe it acquired a large-scale field during a past, more active phase that has stubbornly persisted. In this scenario, even a tiny trickle of accreting matter is enough to keep this pre-existing magnetic field anchored and organized, allowing the black hole's spin to continuously extract energy and power a faint but persistent jet, all while the system appears virtually bald and inactive. Another compelling line of thought suggests that the environment around these black holes is far from empty. It's filled with a hot, magnetized corona. This corona, a tenuous cloud of ultra-hot plasma surrounding the black hole and its disk, could be the hidden source of the required magnetic flux. Even in the absence of a strong accretion flow, turbulence and magnetic reconnection in this corona could maintain a large-scale, ordered magnetic field that connects to the black hole. The jet, in this case, will be launched directly from this coronal plasma, powered by the black hole's spin and sustained by the magnetic energy reservoir of the corona itself. This would make the jet independent of the meager accretion flow, a self-sustaining phenomenon that can persist long after the main feast has ended. It transforms our view of the jet from a direct product of accretion to a more resilient feature, one that can endure through periods of starvation by drawing on different resources. The existence of these bald, jet-producing black holes carries profound implications for the life cycle of supermassive black holes and their host galaxies. It suggests that the jet feedback mechanism we've discussed is not just an occasional cataclysm that happens during brief, bright phases of activity. Instead, it could be a near-constant background process. Even when a supermassive black hole is not visibly feasting, its faint, spin-powered jet could be steadily injecting a small but persistent amount of energy into the surrounding galactic halo. This would act like a low-grade thermostat, providing a continuous form of heating that helps prevent the hot gas in the galaxy from cooling and collapsing, thereby subtly regulating star formation over billions of years. The brilliant outbursts we love to study might just be the loud, attention-grabbing peaks in a much longer, quieter symphony of feedback, with the bald black holes providing the underlying, steady hum that truly governs the long-term evolution of galaxies. This forces us to reconsider the true duty cycle of jet activity and its integrated impact, suggesting that even the quietest monsters in the darkness may never be truly silent. But even the most perfectly launched jet is not immune to the forces of chaos that seek to tear it apart from within, which brings us to the turbulent world of instabilities and kink modes. Imagine a fire hose pumping water at an unimaginable pressure. If the hose itself is not perfectly reinforced, the stream will begin to whip and snake uncontrollably. Now scale that image up to a beam of plasma stretching across millions of light years, and you begin to grasp the monumental forces at play. These are not simple bends, they are violent, wave-like distortions that can ripple through the jet structure, causing it to wobble, constrict, and in some catastrophic cases, completely disrupt and dissipate its energy into the surrounding void. The fact that we see any straight jets at all is a testament to some powerful, stabilizing force fighting a constant, invisible war against this inherent turbulence. The primary instabilities that plague these cosmic beams fall into two broad but interconnected categories. The first are hydrodynamic instabilities, which are governed by the sheer motion and pressure of the flowing plasma, much like the instabilities that form in a fast-moving river or the exhaust of a rocket. If the jet is moving much faster than the speed of sound in the surrounding medium, which it almost always is, it creates a turbulent boundary layer where the two gases mix. This can lead to the jet's surface becoming ragged and unstable, slowly eroding its outer layers. The second, and often more dramatic, class are the magneto-hydrodynamic instabilities. Here, the magnetic fields that are so crucial for the jet's existence can also become the source of its destruction. The most famous of these is the kink instability. Picture the jet's central, fast-moving spine as a long, flexible cord. If the magnetic pressure inside this cord is greater than the external confining pressure, the cord can suddenly buckle and twist into a helical, corkscrew shape. It's like overinflating a bicycle tire tube. The internal pressure causes it to bulge and warp in unpredictable ways. In a jet, a full-blown kink mode doesn't just bend the beam. It can pinch it off entirely, disrupting the flow and turning a focused energy beam into a chaotic, dissipating plume. This immediately raises a pivotal question. Why do some jets, like the legendary one in the galaxy M87, appear remarkably straight and stable for their entire observable length, while others look like twisted, knotted ropes, riddled with bright spots where these instabilities are running wild? The answer seems to lie in a delicate cosmic balancing act between the jet's internal and external pressures. A jet can be thought of as a long, thin balloon of magnetized plasma. For it to remain stable, the external pressure from the intergalactic medium must provide a firm, confining wall. If this external pressure drops too low, perhaps because the jet has traveled into a particularly empty region of space, there is nothing to prevent the jet's own internal pressure from causing it to balloon outward and become unstable. Conversely, a jet with a very strong, orderly internal magnetic field can provide its own confinement. The magnetic field lines wound tightly around the jet's axis, create a kind of tensile strength, a magnetic tension that resists bending and helps the jet maintain its integrity even as it plows through an uneven environment. The straightest jets are likely those blessed with both a supportive external pressure and a powerful, internally generated magnetic corset. What we observe as bright knots and flares within a jet may often be the visible symptoms of these instabilities at work. A kink instability doesn't just distort the jet's shape, it compresses the plasma and magnetic fields at the points of greatest bending. This compression acts like a natural particle accelerator, driving shocks that energize electrons to extremes, causing those specific segments to blaze with synchrotron radiation. In this light, a knotted, wiggling jet is not necessarily a dying jet. It might be a jet in a state of constant, energetic readjustment, where magnetic energy is being converted into particle acceleration and light through its very struggles. The stability of a jet, therefore, is not a permanent state but a dynamic condition. A jet might start its journey stable, only to develop a kink mode further out as the confining pressure drops or as internal magnetic stresses build to a breaking point. Understanding these patterns is like reading the jet's vital signs, giving us a direct window into the invisible pressures and magnetic forces that govern its epic journey from the black hole to the edge of intergalactic space. This brilliant two-step process for creating gamma rays immediately leads us to a deeper and more subtle puzzle. Where do these humble seed photons actually come from? Identifying the origin of these low-energy particles is absolutely critical because the entire efficiency and character of the gamma ray factory depends on their source. It's the difference between a manufacturing plant that uses raw materials from its own backyard versus one that has to import them from a distant continent. The entire operation changes based on that single decision. For decades, astronomers have been piecing together this cosmic supply chain, and it turns out there are three primary suppliers, each one leaving a distinct signature on the final high-energy product. The first and most straightforward supplier is the jet itself through its own internal synchrotron radiation. This scenario, known as the synchrotron self-Compton model, is a marvel of self-sufficiency. The same population of ultra-fast electrons that produces the jet's radio and optical light by spiraling around magnetic fields also uses that very same light as raw material. Those synchrotron photons become the targets for a second round of collisions, where the electrons boost them into the gamma ray regime. It's a beautifully closed loop. The jet creates its own fuel for its most energetic output. The key signature of this internal supply is a very tight correlation between the low-energy synchrotron flare and the high-energy gamma-ray flare. If you see the jet brighten in visible light and then, almost immediately, brighten in gamma rays, it's a strong indicator that the same batch of electrons is responsible for both, using its own synchrotron emission as the seed photons. This model works exceptionally well for many blazars, where the jet is pointed right at us and its internal emission dominates our view. However, the jet doesn't always operate in a vacuum. The second major supplier is the external environment surrounding the black hole, primarily the dazzlingly bright accretion disk. This disk, with its immense surface area, floods the central regions of the active galaxy with a torrent of ultraviolet and X-ray photons. If the gamma-ray producing region of the jet is located close to the black hole, it is bathed in this intense external radiation field. When a relativistic electron in the jet collides with one of these powerful disk photons, the resulting inverse Compton boost can be tremendous, creating gamma rays of the highest energies. There's also the fascinating contribution from the broad line region, the dense clouds of gas orbiting the black hole that are illuminated by the accretion disk. These clouds reprocess the disk's ultraviolet light into a wider field of lower energy optical emission, providing another pervasive source of external seeds. The telltale sign of this external supply is a different timing pattern. A flare in the accretion disk might take time to propagate and influence the jet, potentially causing a delayed gamma-ray flare. Furthermore, the specific spectrum of the gamma rays can reveal the original energy of the seed photons, acting as a fingerprint that points back to the hot disk or the cooler broad line region clouds as the primary source. The third supplier is the most universal and ghostly of all, the cosmic microwave background radiation. This is the faint afterglow of the Big Bang, a nearly uniform bath of cool microwave photons that permeates every cubic centimeter of the universe. On its own, this background radiation is incredibly feeble, but special relativity introduces a dramatic twist. For a blob of plasma in a jet that is moving at 99.9% of the speed of light directly towards us, this quiet cosmic hum is transformed. Due to an effect called relativistic aberration, the entire universe appears to be focused into a bright, head-on beam. From the perspective of the electrons in that fast-moving blob, the cosmic microwave background is no longer a cool microwave glow. It is blue-shifted into a brilliant, intense spotlight of infrared and optical photons. This suddenly makes the ancient echo of creation a potent source of seed photons. This mechanism is particularly important for the most powerful jets that extend far beyond their host galaxies, where the internal synchrotron radiation has faded and the light from the accretion disk is left far behind. In these vast, lonely reaches, the jet can still produce gamma rays by upscattering the one light source that is always there, the fossil light of the universe itself. The profound challenge and the heart of the mystery is that for any given jet flare, these three different seed sources can produce gamma ray signals that are frustratingly similar. From our distant vantage point, a spike on our gamma ray detector doesn't come with a label stating its origin. To unravel this, astronomers must become master detectives, looking for subtle clues in the correlated behavior across the entire electromagnetic spectrum. They build sophisticated models that test different seed photon scenarios against the data. If a gamma ray flare occurs with no corresponding change in the jet's own synchrotron emission, it points strongly to an external seed source like the accretion disk. If the gamma ray spectrum is particularly hard and energetic, it might indicate that the seeds were the high-energy photons from the disk itself, rather than the jet's softer synchrotron light. The answer is rarely clear-cut, and it's likely that in many jets all three sources contribute to varying degrees, their relative importance shifting as the jet evolves and as different regions within it flare into activity. Pinpointing the dominant seed supplier is not just an accounting exercise. It allows us to map the jet's structure, determine how far from the black hole the gamma rays are produced, and finally understand how these cosmic engines interact with their environment on every scale, from the immediate fury of the accretion disk to the vast, quiet backdrop of the entire cosmos. Stepping back from the intricate mechanics of the jet itself, we arrive at a mystery that spans the entire cosmos, connecting the furious outburst of a single black hole to the grandest architecture of the universe. This is the strange and compelling alignment between some jets and the cosmic web, the vast filamentary network of dark matter and gas that forms the skeleton of the universe. On the largest scales, matter is not distributed randomly. It forms a cosmic spiderweb with long, thin filaments connecting dense nodes where thousands of galaxies swarm in massive clusters. The spaces between these filaments are immense, near empty voids. For decades, astronomers have noticed that in certain galaxy clusters, the powerful radio jets and their gigantic lobes appear to be pointed with an uncanny frequency directly along these cosmic filaments, as if the black hole is using the universe's own superhighways to channel its energy. This is more than a curious pattern. It's a potential clue that the growth of the largest structures in the universe is intimately tied to the violent activity at the hearts of its constituent galaxies. One of the most straightforward explanations for this alignment is that it's not the jet dictating the direction, but the environment itself guiding the jet. Picture a supermassive black hole sitting at the center of a galaxy that is itself falling into a massive cluster. The galaxy isn't moving through empty space. It's traveling along a filament, a river of dark matter and gas that defines its path. The accretion disk around the black hole is fed by this intergalactic gas, and the disk's orientation is thought to be shaped by the direction from which this fuel arrives. If gas is funneled onto the black hole predominantly from along the filament, the resulting accretion disk will naturally align itself with this flow, and since jets are launched perpendicular to the disk, they too will point along the filament's axis. It's a process of cosmic conformity, where the large-scale flow of matter in the universe sets the spin axis of the black hole, turning it into a naturally aligned beacon. In this scenario, the alignment is a product of the black hole's diet, with the richest food source arriving from a specific direction dictated by the cosmic web. However, the plot thickens considerably when we consider the alternative, that the causality might actually run in the opposite direction. What if the jet is not a passive passenger but an active sculptor? This leads to a truly profound possibility that these aligned jets are a primary feedback mechanism for building the cosmic web itself. The filaments of the cosmic web are filled with a tenuous but extremely hot gas, known as the warm-hot intergalactic medium. For this gas to collapse under gravity and fuel the growth of galaxies and clusters, it must somehow cool down. But the jets, by pumping tremendous energy directly into these filaments, can keep the gas hot and prevent it from cooling. An aligned jet acts with maximum efficiency here. Its energy is injected directly into the dense filamentary highway, heating it along its entire length and effectively putting a brake on the flow of gas toward the cluster's center. In this view, the alignment is not a coincidence but a self-regulating feature of cosmic evolution. The black hole, by aligning its jet with the filament, is actively regulating its own fuel supply and the growth of the entire large-scale structure, preventing the system from over-consuming and growing too rapidly. The observational challenge in unraveling this mystery is immense, as it requires mapping both the invisible cosmic web and the orientation of jets across vast distances. We cannot see the dark matter filaments directly. Instead, we infer their presence by meticulously charting the positions and motions of millions of galaxies. When we overlay these maps with the positions and directions of powerful radio jets, the statistical evidence for alignment, particularly in the densest environments, is growing. But proving a causal link is another matter entirely. Is the alignment more common in younger clusters that are still forming, suggesting the jet is responding to the environment? Or do we see the alignment specifically in clusters where star formation has been quenched, hinting that the jet has already done its work and shut down growth? The answers to these questions are still buried in the noise of large astronomical surveys, requiring ever more sophisticated statistical analyses to uncover. This grand-scale alignment forces us to confront the role of black holes not as isolated monsters, but as integral components of the cosmic ecosystem. Their explosive energy, channeled by the architecture of the universe itself, may be the very force that maintains the delicate balance between the relentless pull of gravity and the dispersing effect of heating, shaping the distribution of matter on the very largest scales. The jet, therefore, becomes more than a spectacular outburst. It is a cosmic regulating valve, and its puzzling alignment with the cosmic web is a signature of its profound role in the billion-year story of how the universe built its largest structures. This incredible effect, where a jet's motion literally sculpts the light we receive, brings us to a cornerstone concept in high-energy astrophysics: relativistic beaming. Imagine a lighthouse, but one where the light beam isn't just rotating. It's being physically squeezed and intensified by the lighthouse's own fantastic speed. That's essentially what happens to the emission from a black hole jet. As the jet's material races toward us at over 99.9% of the speed of light, the very nature of light emission transforms due to Einstein's special theory of relativity. The radiation, which would normally spray out in all directions, gets compressed and focused into a narrow cone pointing directly along the jet's direction of motion. It's a dramatic amplification, a cosmic spotlight that can make a jet pointed our way appear hundreds or even thousands of times brighter than an identical jet pointed in any other direction. This isn't just a slight brightening, it's a fundamental distortion of reality as we observe it, making certain jets seem like the most powerful objects in the universe when, in fact, we might just be looking straight down the barrel. The physics behind this is a breathtaking combination of two relativistic effects. The first is the Doppler effect, familiar from the changing pitch of a passing siren. As a light source moves toward you, its waves are compressed, shifting its light to higher frequencies and making it appear bluer and more energetic. For a jet approaching at near light speed, this blue shift is extreme. But relativity adds a second, even more powerful ingredient: time dilation. From our perspective, the clock on the fast-moving jet appears to be ticking slower. This means the individual particles in the jet seem to radiate their energy over a longer period of time, which would tend to make the source appear dimmer. However, this time-stretching effect is more than counteracted by a third geometrical effect, the headlight effect. Because the jet is moving so fast, the photons it emits are beamed forward, piling up in the direction of motion. The combination results in a tremendous frequency-dependent boost in brightness. The emission is intensified and its peak is shifted to much higher energies. For a jet coming directly at us, this relativistic beaming can inflate its apparent luminosity to levels that utterly dwarf its true intrinsic power, creating an illusion of cosmic proportions. This dramatic brightening is the very reason we have a special class of objects known as blazars. A blazar is simply an active galaxy whose jet is fortuitously aligned almost perfectly with our line of sight. We are staring directly into the cosmic blowtorch. Because of this, blazars dominate the high-energy sky. They are the most commonly detected sources of extragalactic gamma rays, and they exhibit the most violent and rapid variability. But this gift of a bright, well-aligned source is also the source of a profound and enduring problem in cosmology, the beaming bias. Our entire census of the universe's most energetic phenomena is heavily skewed by this effect. We are, in a very real sense, only seeing the jets that are pointed at us. For every one brilliant blazar we detect, there could be hundreds or even thousands of similar active galaxies with identical black holes and jets that we completely miss because their beams are pointed away from Earth, their light dimmed by the same relativistic physics that makes the blazar so dazzling. We are trying to understand the true population of these engines by only studying the rare, screaming outliers. This bias creates a monumental challenge for understanding the true power distribution and life cycle of supermassive black holes. When we calculate the immense energy output of a blazar, are we measuring the true power of the central engine, or are we just witnessing a fantastically amplified version of a much more common and perhaps quieter phenomenon? The answer dictates how we model the role of jets in galaxy evolution. If most jets are far less powerful than the blazars suggest, then their collective impact on heating the intergalactic medium and regulating star formation might be more modest. However, if the blazars are genuinely representative of the raw power these engines can produce, then our understanding of black hole feedback needs to account for these titanic, albeit rare, outbursts. It forces astronomers to employ clever statistical methods to correct for this beaming bias, to essentially estimate how many unseen, misaligned jets must exist for us to see the small number of beamed ones that we do. This is like trying to determine the true height of a population by only measuring the players in the NBA. Your sample is heavily biased toward the extremely tall, and you must use complex models to infer the characteristics of the general population you never see. The problem deepens when we consider that the beaming effect is not a simple on-off switch. It has a strong dependency on the jet's exact speed and its angle to our line of sight. A jet moving at 99% of light speed that is pointed just 5 degrees away from us will appear vastly brighter than an identical jet pointed 15 degrees away. This creates a smooth continuum of apparent brightness, from the hyperluminous blazars to the much fainter radio galaxies whose jets are pointed at wider angles. Disentangling this angle-speed brightness degeneracy is incredibly difficult. We might observe two galaxies with very different apparent jet powers and assume they have fundamentally different engines, when in reality they could be identical twins, with one simply having its jet pointed more directly at us. This makes it nearly impossible to classify these systems and understand their evolution without independent measures of the jet's intrinsic speed, which are themselves extremely challenging to obtain. Ultimately, the relativistic beaming effect is a double-edged sword. It provides us with our clearest, most detailed view into the inner workings of a jet's accelerator, giving us a front-row seat to the most violent and variable processes in the universe. Yet, at the same time, it presents a fundamental obstacle to obtaining a complete and unbiased picture of the black hole population. It reminds us that our view of the cosmos is not a perfect objective map, but a perspective distorted by the very laws of physics that govern it. We are left to carefully deconstruct the illusion, separating the true nature of these dark engines from the brilliant, relativistic mirage they project across the universe. One of the most persistent and practical puzzles in the life of a black hole jet is the constant struggle of its high-energy electrons against a universe that seems determined to drain them of their power almost as soon as they receive it. These electrons are the glittering workforce of the jet, responsible for the brilliant synchrotron radiation that illuminates its path from radio waves up to X-rays. But this brilliance comes at a steep and continuous cost. Every time an electron spirals around a magnetic field line to emit a photon of synchrotron light, it loses a tiny fraction of its precious kinetic energy. This process, known as radiative cooling, acts like a constant, invisible tax on the electron's speed. In the dense, magnetically intense regions near the base of the jet, this cooling can be catastrophically fast. An electron accelerated to a fantastic energy near the black hole could radiate away 99% of that energy in a matter of hours or days, a fleeting moment on the cosmic timescale of the jet's million-year journey. If this were the whole story, the jet would appear brilliantly bright at its launch point and then fade into darkness and invisibility after just a short distance, its light extinguished as its electrons ran out of steam. Yet, this is not what we observe. We see jets that remain luminous, often with bright, shining knots across their entire incredible length, spanning hundreds of thousands of light years. This simple, glaring contradiction reveals a fundamental truth. The jet cannot be a simple fire hose spraying pre-accelerated particles into the void. Instead, it must be riddled with hidden, in situ particle accelerators, a chain of cosmic booster stations that constantly re-energize the fading electrons and keep the entire structure shining. The primary cooling mechanisms are a devastating one-two punch from the very processes that create the jet's light. The first is the synchrotron radiation itself. The rate of this energy loss is ruthlessly efficient, depending on the square of the electron's energy and the square of the magnetic field strength. In a powerful jet with strong magnetic fields, an ultra-relativistic electron is like a rapidly spinning top on a rough surface. It bleeds energy at a ferocious rate, its frantic dance slowing down perceptibly with every passing moment. The second punch comes from inverse Compton scattering. The same high-speed electron that is producing synchrotron light is also surrounded by a sea of photons, both its own synchrotron emission and external light from the accretion disk or the cosmic microwave background. When the electron collides with one of these photons and boosts it to gamma-ray energies, the electron itself recoils, surrendering a significant amount of its own kinetic energy in the process. It's a double-edged sword. The very act of creating the jet's most energetic radiation also serves to cool down the electrons that make it possible. The combined effect of these two processes defines a critical timescale known as the cooling time. For the highest energy electrons responsible for the X-ray and gamma-ray emission, this cooling time can be astonishingly short, sometimes less than the time it takes light to travel from one end of the jet's visible feature to the other. This means that the electrons producing the light we see in a given part of the jet simply cannot have been accelerated at the black hole. They must have received their immense energy very recently and very locally. This leads to the inescapable conclusion that the jet is not a passive pipeline but a dynamic and internally active structure. The electrons are not just passengers on a relativistic express train. They are being repeatedly shoved back up to speed at various points along the route. The bright knots we so often observe are almost certainly the locations of these reacceleration sites. The leading theory for how this happens points to shocks. Imagine the jet's flow is not perfectly smooth. The central engine might hiccup, sending a faster moving parcel of plasma downstream. this faster blob will eventually catch up to a slower moving parcel ahead of it. When they collide, they don't merge gently, they create a shock front, a sharp discontinuity where the plasma is suddenly compressed, heated, and its magnetic field is amplified. This shock wave acts as a powerful and efficient natural accelerator. Charged particles can bounce back and forth across this magnetic barrier, trapped by the turbulence, and each crossing gives them a small boost of energy. This process, known as diffusive shock acceleration, can take lethargic, cooled electrons and whip them back up to relativistic speeds, causing that specific segment of the jet to blaze with new light. In this view, each luminous knot is a testament to a recent traffic jam in the flow, a cosmic collision that has reinvigorated the jet's glow. However, the shock model, while compelling, is not the entire solution. Observations reveal complexities that this simple picture struggles to explain. For instance, we see diffuse, widespread emission between the bright knots, a faint but persistent glow that suggests a more continuous, low-level reacceleration is also at work throughout the jet's volume. This points to a second, more subtle mechanism, turbulent acceleration. The interior of the jet is likely a maelstrom of chaotic motion, with magnetic field lines constantly tangling, breaking, and reconnecting. This turbulence creates a sort of magnetic froth, where particles can get a random kick from interacting with swirling magnetic eddies. It's a less efficient process than an organized shock, but it operates throughout the entire jet, providing a steady background of re-energization that keeps the electrons from cooling completely in the vast spaces between the major knots. This turbulent soup might also be responsible for the mysterious sharp edges and filamentary structures we see in some jets, as these complex magnetic dynamics can confine and shape the plasma in ways a simple flow cannot. The ultimate mystery is that we still do not have a complete map or a full understanding of where and how all this reacceleration occurs. The precise microphysics of how particles gain energy in a turbulent plasma or at a shock front is a frontier of plasma physics itself. Furthermore, the relative importance of large-scale shocks versus widespread turbulence is likely different from one jet to another and may even change over time within a single jet. A young, powerful jet from a violently feeding black hole might be dominated by internal shocks from frequent engine hiccups, while an older, more stable jet might rely more on turbulent motions to maintain its faint glow. This ongoing need for in situ acceleration transforms our perception of the jet from a simple beam of light into a living, breathing entity. It is a complex ecosystem where order and chaos interact, where the immense power from the central black hole is continuously reprocessed and renewed through a series of hidden, distributed engines, ensuring that its brilliant scream across the cosmos never fades into silence. Even as we grapple with the invisible engines and chaotic interiors of these jets, a simple, elegant classification system reveals a fundamental split in their very appearance. When astronomers began systematically mapping the sky with radio telescopes, they noticed that extended radio galaxies fell into two clear and distinct camps, a division so robust it was enshrined as the Fanaroff-Riley classification. On one side, we have the FR1 jets. These are the cosmic fog banks. They are brightest and most luminous close to the galactic core, near the supermassive black hole that births them. From that point, their radio emission gradually fades and becomes more diffuse as you follow them outward, blurring into a wide, plume-like structure without a clear, concentrated endpoint. They are like a powerful river delta, spreading its energy and sediment over a vast area as it meets the sea. In stark contrast, FR2 jets are the cosmic blowtorches. They appear relatively dim and unassuming as they emerge from the core, but all their power is focused into their dramatic, edge-brightened conclusions. They travel vast distances with incredible precision, finally terminating in intensely bright, compact regions known as hotspots, where the jet slams into the intergalactic medium. These hotspots are often connected back to the core by giant, symmetrical lobes that act as vast reservoirs for the jet's energy. The dividing line between these two families is not fuzzy. It's a sharp threshold in radioluminosity. If a radio galaxy is above a certain power, it's almost certainly an FR2 with those characteristic hotspots. If it's below that line, it's an FR1. This clear dichotomy screams that a fundamental switch is being flipped in the black hole's engine room, a transition that changes the jet from a turbulent, dissipative flow into a focused, penetrating sphere. The immediate suspect for this great divide is the raw power of the jet itself. An FR2 jet is by definition a high-power engine. It possesses so much kinetic energy and momentum that it can punch through the ambient gas of its host galaxy and its halo with minimal disruption. It remains a cohesive, supersonic bullet all the way to its end, only meeting its match when it finally rams into the much denser intergalactic medium far from the galaxy. This final, violent collision at the terminus creates the brilliant hotspot, a site of immense particle acceleration and shock heating where the jet's forward progress is abruptly halted and its energy is splattered outward to inflate the giant radio lobes. It's a clean, efficient, and highly structured way to deposit energy. An FR1 jet, however, is a lower power affair. It's like a weaker stream of water from a hose that begins to break up into droplets almost immediately. It lacks the thrust to maintain a stable, fast spine over long distances. As soon as it begins its journey, it starts to interact strongly with the denser galactic environment, becoming decelerated and turbulent. This causes it to dissipate its energy early and along its entire length, which is why it's brightest near the core and fades into a diffuse plume. The FR1 jet is effectively dying a slow death from the moment it's born, victim of 1,000 tiny frictional losses, while the FR2 jet triumphs over its local environment to make its mark on the intergalactic scale. However, power alone cannot be the entire story. The environment through which the jet travels must also play a decisive role. Imagine two jets with identical power output from their central black holes. One resides in a massive, gas-rich elliptical galaxy sitting at the center of a dense galaxy cluster, surrounded by a vast, hot atmosphere. The other lives in an isolated galaxy drifting through a relatively empty galactic void. The first jet, the one in the dense cluster, will have to fight its way through a thick, resisting medium from the very start. Even if its engine is powerful, this external pressure could disrupt its flow, causing it to decelerate and become turbulent, potentially forcing it into an FR1 morphology. The second jet in the sparse environment might have a clear path, allowing it to remain collimated and form the classic FR2 hotspots, even if its intrinsic power is somewhat lower. This suggests that the FR classification is not just a label for the jet, but a diagnostic of the entire system. The balance between the thrust from the black hole and the pressure of the surrounding cosmic weather. An FR1 might simply be an FR2 that was born into a much tougher neighborhood, its brilliant potential stifled by the dense gas that surrounds it. Yet another layer of complexity points to the jet's own internal composition and stability. The transition from a successful, hotspot-forming FR2 to a floundering, plume-like FR1 might occur when the jet becomes subsonic. A powerful FR2 jet is highly supersonic. It moves much faster than the speed of sound within its own plasma and the surrounding medium. This allows it to maintain a sharp, well-defined shock front at its termination point. If a jet slows down enough, whether due to lower power or a higher resistance, it can cross a critical threshold and become subsonic. When this happens, it loses the ability to form a strong, confined terminal shock. Instead of a focused hotspot, the energy dissipates through a series of weaker, disorganized shocks and turbulence along its body, creating the diffuse appearance of an FR1. This is akin to the difference between a supersonic bullet creating a clean hole and a subsonic projectile creating a splatter. The stability of the jet against internal kink instabilities, which we discussed earlier, is also a factor. A less magnetically stable jet might be more prone to disrupting itself, contributing to the early energy dissipation seen in FR1s. The profound and unresolved mystery is that these factors, jet power, environmental density, and internal stability, are all deeply intertwined. We cannot run a controlled experiment on a supermassive black hole, tweaking one parameter while holding the others constant. The observed FR divide is the final, complex outcome of this interplay. Is the primary driver the black hole's spin, which dictates the jet's power? Is it the density of the galactic halo, which determines how far the jet can travel before being disrupted? Or is it the accretion state, which might influence the jet's magnetic field structure and internal robustness? The answer is almost certainly all of the above, but we lack a precise formula that predicts exactly which morphology will emerge from a given set of initial conditions. This classification, while beautifully simple on the surface, points to a universe of hidden physics governing the transition from order to chaos, from a perfectly focused beam to a disorganized plume, reminding us that even the most colossal structures in the cosmos are shaped by the delicate balance between their inner fire and the outer forces they must confront. But this search for cosmic accelerators brings us to a truly fundamental question: just how powerful can these engines become? Is there a natural limit to the energy they can bestow upon a single particle? And could this extreme realm be the origin of the most baffling messengers from the cosmos, the ultra-high-energy cosmic rays? These are not your average cosmic rays. We are talking about individual subatomic particles, protons or atomic nuclei, carrying kinetic energy equivalent to a well-thrown baseball, all compressed into a vanishingly small speck. The sheer existence of such particles is a monumental puzzle, as their energy is millions of times greater than what the most powerful particle colliders on Earth can produce. To create them requires an accelerator of almost unimaginable scale and ferocity, and black hole jets stand as one of the very few structures in the universe that even come close to qualifying for the job. The theoretical framework for understanding this ultimate limit is encapsulated in a beautifully simple yet powerful concept known as the Hiller's criterion. Named after the astrophysicist who first proposed it, this criterion provides a basic yardstick for any candidate cosmic accelerator. The core idea is that to confine a charged particle within an acceleration region long enough for it to reach an extreme energy, two things are needed: a strong magnetic field and a vast amount of space. The particle being charged is tied to the magnetic field lines spiraling around them as it gains energy. If the accelerator is too small, the particle will simply escape before it has reached its maximum potential. The Hiller's criterion neatly defines the minimum size required for a given magnetic field strength to accelerate a proton to a specific energy. To reach the very highest energies we observe, around 100 electron volts, an accelerator needs a magnetic field of microgauss strength about the same as the Milky Way's average field, but extended across a mind-boggling distance of 30 million light-years. Alternatively, a much smaller region with a correspondingly stronger magnetic field could also do the trick. It's a cosmic balancing act between magnetic might and physical scale. So where do black hole jets fit into this picture? Their credentials are undeniably impressive. Consider the colossal radio lobes they inflate, often stretching for hundreds of thousands of light years. These lobes are filled with turbulent, magnetized plasma, providing a potential acceleration site that is vast beyond comprehension. While their magnetic fields might be weaker than those at the jet's base, the sheer volume of these structures could allow particles to be trapped and accelerated over immense timescales. The shock waves at the jet's termination point, where it violently rams into the intergalactic medium, are prime locations for this process, acting as natural particle cannons on a galactic scale. On the other end of the spectrum, the base of the jet itself offers a different set of advantages. Here, closer to the black hole, magnetic fields can be phenomenally strong, potentially billions of times more powerful than a typical refrigerator magnet. While this region is much more compact, the intense field strength could, in theory, accelerate particles to tremendous energies in a very short distance. The jet, therefore, presents a two-stage solution: a small, powerful accelerator near the engine for a rapid initial boost, and a massive, sprawling reservoir in the lobes for a final, epic push to the absolute brink of what is physically possible. Yet, for all their might, jets may still fall agonizingly short of the theoretical Hiller's limit for the very highest energy events. The universe itself places a firm cap on how far these particles can travel, known as the Greisen-Zatzepin-Kuzmin or Giesecke cutoff. A proton with an energy exceeding about 6 times 10 to the 19th electron volts is so powerful that it can interact with the faint, leftover photons from the Big Bang, the cosmic microwave background. In these collisions, the proton loses energy by creating new particles, like a marathon runner constantly having to push through a dense, sticky fog. This means that any ultra-high-energy cosmic ray we detect on Earth must have originated from a source relatively nearby, within our local supercluster of galaxies, or else it would have been slowed down by this cosmic background radiation over intergalactic distances. This presents a profound challenge for the jet hypothesis. When we look around our cosmic neighborhood, we do not see an obvious, hyper-powerful jet source that neatly aligns with the arrival directions of these ultra-energetic particles. The sources appear to be transient, or perhaps the particles' paths are scrambled so thoroughly by intergalactic magnetic fields that tracing them back is nearly impossible. This leads to a fascinating and ongoing debate. Could it be that the most extreme cosmic rays are not produced in the steady, long-lived lobes, but in brief, cataclysmic eruptions from the jet's core? A sudden, violent event like a massive magnetic reconnection episode near the black hole could create an electric field of staggering intensity, acting as a lightning bolt that impulsively accelerates a small number of particles to energies that temporarily surpass the steady-state limits. Alternatively, perhaps multiple weaker shocks within the jet can work in concert, a process known as multiple shock acceleration, where a particle gains a series of smaller boosts from successive shock fronts, gradually climbing to an energy that a single shock could never provide alone. The jet, in this view, is not a single monolithic accelerator, but a complex multi-stage machine where different mechanisms dominate at different points, all conspiring to push the boundaries of particle energy. The mystery of ultra-high-energy cosmic rays therefore remains a powerful driver of discovery, forcing us to look at these familiar jets in a new light, searching for the fleeting, violent moments when they become the most powerful particle accelerators in the entire universe. Now we arrive at a mystery that connects the silent ripples in the fabric of space-time to the most brilliant screams of light in the cosmos, the profound, and still largely theoretical, connection between gravitational waves and black hole jets. For all their immense power, the jets themselves do not produce detectable gravitational waves. Their energy is channeled into light and kinetic fury. But the colossal engines that launch them absolutely do. We are on the cusp of a new era where we will not only see the aftermath of a black hole's power, but also feel the very vibrations of its birth and transformation, opening a window into the most violent moments of a jet's life that has been permanently closed until now. The primary source of these space-time ripples will be the ultimate cosmic dance, the merger of two supermassive black holes. Picture a binary system, two dark giants millions or even billions of times the mass of our Sun, slowly spiraling toward each other over eons. As they orbit, they strain the space around them, emitting a steady, low-frequency hum of gravitational waves. In the final, breathtaking moments before they coalesce into a single, more massive black hole, This hum swells into a cosmic crescendo, a brilliant chirp of gravitational radiation that will be the prime target for future observatories like the Laser Interferometer Space Antenna, or LISA. This merger is not a gentle event. It is the most violent transformation a black hole can undergo. The new, single black hole that emerges from this union is born screaming, its properties of mass and spin forged in an instant of unimaginable violence. And it is precisely in this chaotic aftermath that the conditions for launching a jet are likely created or utterly transformed. This is where the potential for a revolutionary discovery lies, in the combination of a gravitational wave signal with a simultaneous electromagnetic observation of a newborn jet. Imagine LISA detecting the telltale chirp of a supermassive black hole merger in a distant galaxy. Within hours or days, telescopes across the world and in space swivel to that same patch of sky, and there it is, a brilliant new flare of radiation, the signature of a jet being launched or re-energized from the newly merged black hole. This single, coordinated observation would be worth more than a century of isolated data. The gravitational wave signal would provide a direct, immutable readout of the black hole's fundamental parameters. From the waveform, we could extract the precise masses of the two original black holes and the mass and spin of the final, merged object. No more indirect, model-dependent inferences. We would know with stunning accuracy the exact properties of the engine right at the moment a jet was ignited. The information encoded in that spin measurement would be particularly transformative for our understanding of jet formation. One of the biggest theoretical questions is how the merger process affects the black hole's rotation. Does the violent collision typically produce a maximally spinning black hole, a perfectly charged battery for the Blandford-Zenagic process, or is the result often a more slowly rotating object which would struggle to launch a powerful jet? A single coincident detection would answer this definitively. If we consistently see jets flaring after a merger, and the gravitational wave data shows the final black hole has a high spin, it would be the most direct evidence imaginable that spin is indeed the crucial on switch for these relativistic beams. It would confirm that the energy source is the black hole's own rotation, tapped via its twisted magnetic fields, turning a key theoretical pillar into an observed fact. Beyond just confirming the engine, this multi-messenger approach could unravel the mystery of how the jet's magnetic architecture is built in the chaos following a merger. The accretion disks of the two original black holes would be violently disrupted and merged along with their central monsters. This would create a fantastically turbulent and complex magnetic environment. A gravitational wave signal timed with a jet observation would allow us to witness in real time how quickly this magnetic field can reorganize itself into the large-scale, ordered structure needed to launch a coherent beam. Does it happen in a matter of days, suggesting a rapid and efficient process, or does it take much longer, implying a more gradual buildup? The timing and properties of the jet's electromagnetic flare would hold the answers, giving us an unprecedented view into the dynamics of the engine room during its most volatile state. There is also the thrilling possibility of witnessing a jet being born with a brand new orientation. The spin axis of the final, merged black hole may not align with the spin axis of its progenitors. The gravitational wave signal can, in principle, reveal the orientation of the black hole's spin. If we then observe a jet pointed in a completely new direction, it would be a direct confirmation that the jet is indeed launched along the black hole's rotational axis, and that this axis can be dramatically reoriented by a merger. This would explain the sudden, dramatic changes in jet direction we see in some galaxies, providing a clear and violent mechanism for why some cosmic engines seem to change their aim across the cosmos. The challenge, of course, is that the low-frequency gravitational waves from supermassive black hole mergers are still just beyond our grasp, awaiting the launch of a space-based detector like LISA. And the event rate for such colossal mergers is uncertain. but the scientific payoff is so immense that it drives the entire field forward. To catch both the tremor in space-time and the flash of light from the same cataclysm would be to witness the universe in two completely different languages simultaneously, translating the silent poetry of gravity into the brilliant narrative of light. It would mark the beginning of a true, multi-messenger understanding of black hole jets, finally allowing us to connect the invisible dynamics of the engine directly to the spectacular phenomena we see illuminating the depths of space. As we've journeyed through the immense lobe-carved cavities that mark the end of a jet's road, a strange and rare breed of these cosmic structures presents a profound puzzle. Imagine following a brilliant jet as it streams out of its galaxy, expecting it to culminate in the usual colossal balloons of radio light, only to watch it simply fade into the darkness of intergalactic space, leaving no trace of a terminal hotspot or an enclosing lobe. These are the naked jets, beams that travel astonishing distances without the typical grand finale, and their existence challenges our most basic assumptions about how a jet's journey must end. The absence of these classic lobes points immediately to the environment the jet is traversing. The formation of a lobe requires a specific kind of resistance. The jet must push against a surrounding medium with enough pressure to force the jet's material to spread out, decelerate, and pool its energy. In a typical galaxy cluster, the intergalactic gas, while incredibly thin, still provides this crucial confining pressure. But a naked jet seems to be traveling through a near-perfect vacuum. It suggests the black hole resides in an immense cosmic void, a region of space so empty that the jet meets almost no resistance. Without a surrounding medium to push against, the jet may simply continue to expand freely, its particles and magnetic field diluting so gradually that they never create the concentrated shock front and subsequent reservoir of a visible radio lobe. It's the difference between a fire hose blasting into a brick wall, creating a dramatic spray, and the same hose spraying into the open air where the water stream simply dissipates quietly. Another compelling possibility is that these jets represent a state of near-perfect stability and balance. Most jets are inherently unsteady. Fluctuations in the central engine's power create internal shocks and surges that disrupt the flow, making it prone to instabilities that cause it to interact violently with its surroundings. But a naked jet could be the product of an exceptionally stable black hole engine, one that has achieved a remarkably steady, low-power output over millions of years. This smooth, laminar flow might be so coherent that it avoids creating the internal shocks that typically lead to bright knots and the subsequent transfer of energy to the external medium. Instead of a series of violent collisions, the jet slips through space like a perfectly streamlined arrow, its energy remaining focused within the beam until it dissipates through gradual, invisible means over distances we can no longer track. Its nakedness, therefore, isn't a sign of weakness, but a signature of supreme internal order. The profound challenge in understanding these systems is their sheer rarity and the difficulty of observing them. A jet without lobes is, by its very nature, far more difficult to detect. The brilliant hotspots and extended lobes are the brightest parts of these systems in radio waves, acting as beacons that draw our telescope's attention. A naked jet lacks these flashy signposts. We often only become aware of them when they are pointed almost directly at us, their emission amplified by relativistic beaming, or when they happen to pass through a faint, unrelated cloud of gas that they briefly illuminate, like a cosmic flashlight beam revealing itself in a dusty room. This observational bias means our sample of naked jets is tiny and possibly not representative, making it incredibly difficult to draw general conclusions about why they exist or what they represent in the life cycle of a supermassive black hole. Their elusive nature forces us to consider whether they are a distinct class of object or merely a fleeting phase in a jet's life. Could a naked jet be the youthful precursor to a full-grown lobe? Perhaps we are catching the system in the first few million years of its activity, before the jet's head has advanced far enough to build up a significant cocoon of shocked material. Alternatively, it might be a dying jet, one whose central engine has recently switched off. The lobes, which can glow for tens of millions of years after the jet ceases, would have already faded from view, while the last vestiges of the jet's beam are still visible as they travel onward into the void. In this scenario, the naked jet is a cosmic ghost, the dying whisper of a once powerful engine, and its observation provides a unique snapshot of the final stages of black hole feedback. Ultimately, the mystery of the naked jets underscores a fundamental truth about these cosmic phenomena. Their appearance is not just a product of the black hole that creates them, but a complex dialogue with the environment they inhabit. They reveal that the intergalactic medium is not a uniform sea, but a patchwork of deserts and oceans with vast empty voids existing alongside dense clusters of galaxies. A naked jet is a direct probe of these cosmic wildernesses, a messenger from the emptiest regions of space. Their existence reminds us that to fully understand the power of the darkness, we must also learn to interpret its silence, to decipher the meaning behind what is not there, and to appreciate that sometimes the most telling features of a cosmic engine are the ones it pointedly fails to create. Yet for all the mysteries we've uncovered, the most thrilling chapter in the story of black hole jets is the one we are just beginning to write, propelled by a new generation of astronomical instruments that will see the universe in ways we once thought impossible. Each of these revolutionary telescopes is designed to attack a different facet of the jet enigma, peeling back layers of the unknown with unprecedented precision and sensitivity, promising to transform our sketches of these cosmic engines into high-definition blueprints. First, consider the quest for sheer resolution, the ability to see the infinitesimally small. The Event Horizon Telescope, which famously delivered the first ever image of a black hole's shadow in M87, is not resting on its laurels. The EHT is a global consortium of radio telescopes that effectively creates an Earth-sized virtual dish, and its next phase is one of aggressive expansion. By adding new telescope sites across the globe and even planning for future space-based components, the EHT aims to achieve a resolution so fine it could finally map the very site where the jet is launched, a region terrifyingly close to the event horizon itself. Imagine being able to watch, in real time, how magnetized plasma is channeled from the inner accretion disk into the base of that relativistic beam. We could directly test the predictions of the Blandford-Zenagic process by measuring the shape and strength of the magnetic fields right at the black hole's pole. We might even catch a glimpse of the mysterious magnetically arrested disk state, witnessing the moment when the magnetic field becomes so strong it chokes off accretion and powers the jet with maximum efficiency. The EHT will move us from inferring the engine's workings to directly imaging its fundamental mechanics, transforming a theoretical sketch into a dynamic movie of matter at the brink of oblivion. While the EHT focuses on the tiny launch pad, the Square Kilometre Array, or SKA, will perform a symphony of sensitivity on a colossal scale. This isn't a single telescope, but a vast network of thousands of antennae spread across 2 continents, designed to be the most sensitive radio observatory ever built. Its sheer collecting area will allow it to detect the faintest whispers from the distant universe, revealing jets in galaxies so far away that their light has been traveling for billions of years. This will let us trace the evolution of jets across cosmic time, answering a fundamental question: did black holes launch jets differently in the early universe when galaxies were first assembling? But the SKA's true power lies in its ability to see the invisible. It will perform Faraday rotation mapping with breathtaking detail, creating 3-dimensional charts of the magnetic environment around thousands of jets. This will finally allow us to understand the chaotic, patchwork magnetic fields we see, distinguishing between the turbulence churned up by a young, active jet and the fossilized remnants of eruptions from eons past. The SKA won't just show us the jets, it will reveal the intricate, magnetized history of their interaction with the cosmos, turning the faintest echoes into a clear story. And then there is the domain of pure, unbridled energy. The Cherenkov Telescope Array, or CTA, represents a quantum leap in our ability to see the universe in the most energetic light, very high-energy gamma rays. Unlike space telescopes that directly detect gamma rays, the CTA uses the Earth's atmosphere as a giant detector. It watches for the fleeting flashes of blue Cherenkov light created when a gamma ray slams into the upper atmosphere, creating a cascade of secondary particles. With over 100 telescopes spread across 2 hemispheres, the CTA will be 10 times more sensitive than any existing instrument of its kind. This means we will finally catch gamma-ray flares from blazars with the statistical power needed to perform true particle physics. The CTA could definitively settle the great leptonic versus hadronic debate by precisely measuring the gamma-ray spectra during flares and searching for the specific signatures of proton-induced cascades. It will catch flares on timescales of minutes, probing the incredibly compact regions where acceleration occurs and putting stringent new limits on the potential effects of quantum gravity. The CTA will see the jet's most violent tantrums in exquisite detail, revealing the fundamental physics of its hidden particle accelerators. But the true legacy of these magnificent instruments will not be a simple list of answered questions. The deeper we peer into the heart of these systems, the more complex and bewildering they become. Every new layer of resolution, every new frequency of observation, reveals phenomena that our current models never predicted. The Event Horizon Telescope might show us that the jet launching region is far more chaotic and dynamic than we imagined, governed by instabilities we don't yet have names for. The Square Kilometer Array could discover entirely new classes of stealth jets, so diffuse and magnetically complex that they challenge our very definition of what a jet is. The Cherenkov Telescope Array might detect gamma-ray flares so rapid and energetic that they force us to invent entirely new mechanisms of particle acceleration. The ultimate lesson these next-generation telescopes will teach us is one of boundless curiosity. They are not just tools for solving the 40 mysteries we've laid out today. They are engines for generating the next 40 and the 40 after that. They guarantee that our journey to understand these magnificent cosmic beams will remain an endless frontier, a perpetual invitation to look deeper and wonder more, reminding us that the greatest mystery of all is the universe's endless capacity to surprise us. And so we've reached the end of our journey through 40 of the universe's most compelling cosmic riddles, a voyage that began at the edge of a gravitational abyss and stretched across millions of light years to the faintest whispers of intergalactic space. We've witnessed the impossible contortions of superluminal motion, listened for the ghostly chatter of neutrinos, and felt the profound silence of dark, quiescent jets. Each mystery we've explored is not an isolated curiosity, but a single thread in a grand cosmic tapestry, intricately weaving together the fundamental forces of gravity, magnetism, and particle physics. The black hole jet emerges not just as a celestial spectacle, but as the ultimate cosmic laboratory, a place where the universe conducts its most extreme experiments, challenging the very limits of our understanding and forcing us to rewrite the rules we thought governed reality. This is not a story with a neat conclusion, but an ongoing scientific epic, one where every answered question seems to pry open the door to 2 more, even more profound, waiting in the shadows. The true significance of these enigmas lies in their deep interconnectedness. We cannot hope to solve the puzzle of the jet's ultra-relativistic speed without first understanding the hidden engine of the black hole's spin. We cannot decipher the signal of a high-energy gamma-ray flare without knowing the secret composition of the jet's plasma. The magnetic fields that launch and guide these beams are the same forces that, when they snap and reconnect, create the violent tantrums of flaring activity. The colossal lobes that heat entire galaxy clusters are the direct result of kinetic energy whose origin we are still struggling to account for. This is not a collection of separate problems, but a single, magnificent puzzle of cosmic engineering, where the physics of the infinitesimally small quantum realm meets the dynamics of the largest structures in the universe. To study a black hole jet is to attempt a grand unification in practice, to see how gravity, electromagnetism, and quantum mechanics dance together in the most violent ballroom imaginable. As we stand at this frontier, armed with revolutionary tools like the Event Horizon Telescope, the Square Kilometer Array, and the Cherenkov Telescope Array, we are not merely passive observers. We are active participants in a grand human endeavor, one driven by a curiosity as relentless as the jets themselves. For centuries, we have looked up at the silent points of light in the night sky and wondered. Today, we point our most advanced instruments at those same points of light and discover that they are not silent at all. They are roaring, twisting, and exploding with secrets. Each mysterious knot in a jet, every inexplicable flare, each strangely aligned lobe is an invitation, a challenge from the cosmos to think deeper, to imagine more wildly, and to never accept that we have finally reached the edge of knowledge. This journey through the unexplained is a powerful testament to the human spirit's insatiable drive to explore. It reminds us that the universe is far stranger, more dynamic, and more wonderfully complex than we could have ever dreamed. The mysteries of black hole jets are not merely academic exercises. They are the very forces that have shaped the evolution of galaxies, that may have seeded the cosmos with the particles for life, and that continue to dictate the fate of matter on the grandest scales. They show us that darkness is not empty. It is filled with structure, energy, and a breathtaking beauty that reveals itself only to those who are persistent enough to look. Our quest to understand them is far from over in many ways. It has only just begun. So now we turn this adventure over to you. Which of these mysteries captures your imagination the most? Is it the ghostly potential of dark, quiescent jets, the mind-bending illusion of superluminal motion, or the cosmic power of feedback that shapes entire galaxies? Let us know in the comments below, and don't forget to subscribe as we continue to explore the universe's greatest secrets together.